All right. So welcome to the Tidyverse data wrangling workshop. Today we're going to be going over how to do some data wrangling in the Tidyverse, which is an important skill. You can't really work with data unless you know how to, work with data and prepare it for use. It's very rare in most contexts outside of a classroom that you're going to be given data that's just sort of ready to go. You're usually going to have to do something to it. And so that's what we're going to be talking about today. Before we get started, 2 links I've already put in the chat there, but let me give them to you again. So here we have the, let's move this. There we go. So here we have the slides you can get yourself if you want to follow along. rpubs.com/nickchk /data_wrangling_tidyverse. That'll bring up the slides for you. And then here is a GitHub repo with the files that we're going to be going through for the example task at the end that we'll walk through together. If you've never been on GitHub, it's worth getting familiar with, especially if you're going to be working with data. It will come back to you. But if you go to this site, github.com/nickch-k /data wrangling workshop files, first of all, there's a link to those slides. You don't have to type in both those URLs. Also, if you go to this green code button and you go download zip, you can download all the files that are in this repository. And with that, let's get going. Let's see if I can have the chat open. Do feel free to ask questions at any time. If I can get the chat, please open chat. Where's the chat? Nope. Oh, alt page. Come on. Why won't you show me the chat? I've only been using Zoom for a year. You'd think this would work. All right, well, it will probably flash something at me if somebody has something to say in the chat. Okay, so data wrangling in the Tidyverse. So first of all, what are we going to go through in this workshop? We're going to be talking about what data wrangling is and how to think about it. A lot of the skills that you're going to learn today are going to translate not just in Tidyverse. We're going to be using Tidyverse, technical tools, but a lot of the stuff we're going to be doing is going to apply whatever you're working in. Whether you end up using some other part of R or Python or Stata or Julia or whatever. And so because some of this stuff is just principles of how to work with data. And a lot of the commands and even command names are the same between different languages. There will be other versions of this workshop. There will be one coming up in a few weeks on data.table in R, which is basically, that means R. The syntax is different. It's a lot faster. It's better for working with big data sets. And then a few weeks after that, there'll be a pandas workshop. So we're going through what data wrangling is and how to do it. We'll be talking about the technical details of how to do it in the Tidyverse, and we'll be doing a walkthrough example. So I will be assuming for this workshop that you have some familiarity with R, not necessarily that you are a power user, but I'm not going to start from the very basics of R. Also, we only have so much time. 3 hours is actually a shockingly short period of time to go through all of data wrangling. But also, as with most technical skills, a lot of this comes down to muscle memory. And, you're not really going to learn how to use this stuff until you start doing it, which is partly what the example that we're going to walk through at the end is going to be about. But I'm going to be focusing more here on exposing you to what the tools are and how they work, as opposed to going through the finer details of how they're used. So I want you to know what's out there so that when you're like, hey, I have this problem I need to solve, you know what to look for the documentation on. And then for the actual implementations or the more specific details, you can look into that documentation. My theory on teaching computer skills is that my comparative advantage, what you can really get in a classroom, is being exposed to stuff, and that the actual part of learning how to do it really has to come from doing it. My recommendation really is to find yourself a project. So once we are done with this, maybe find yourself a data set and think, I'm going to clean this data set, and then do it. And it will be awful, and you'll have to do a lot of Googling, and you'll have to do a lot of trial and error, but by the time you come to the end of that project, you'll be a much better data wrangler, and you'll be a lot better prepared for the project after that. Some notes about the Tidyverse if you've not been using it, or maybe if you have. The Tidyverse functions often return tibbles, which are a form of data frames. Data frames are, of course, the standard R object that store data in a sort of spreadsheet style rectangular format. Tibbles are very much like data frames. They do a lot of the same things. You can work with them in the same ways, but they look nicer when you print them. They're a little bit faster on some operations, and also you can have a list in a column. If you want to store, multiple values in the same column, you can do that. Additionally, throughout this talk, I'll be using the pipe, which looks like this. It's a little % sign and then a greater than sign and then another % sign. What that pipe does is it says, take whatever's on the left of this pipe and make it the first argument of the function on the right of this pipe. And I'll go over some more implementation details on that in a second. Pipe is very handy for chaining operations together, makes code a lot more readable. For example, you can do this. So here is an example of some very nested code where I have a bunch of functions that I'm working with, and you end up with a bunch of sort of a mess of nested functions. What am I doing here? I'm taking the mtcars data, I'm getting the AM variable, I'm taking the mean of that while taking out the missing observations, and then I'm turning that into a printable percentage with the % function. And you see it's so long it even runs off the end of the screen. I can do this with pipes instead. I'm going to take an object and pass it along, sort of like a conveyor belt. So I'm going to take my data set, mtcars. I'm going to pass that to the pull function. Pull takes a variable out of the data set, just like the $ does. And then I'm going to take that variable. I'm going to pass it to the mean function, right? I'm taking this variable that I have. I'm making it the first argument of my mean function, which it is up here, right? You can see that I have mean, and the first thing I put in is the variable. Here I've got the variable, and I'm passing it along to be the first thing in mean, and then specifying that I also want to take out the missings. And then I'm taking that whole mean that I've calculated, I'm passing it along to my % function, which will turn it into a percentage to print out as a nice string. This makes your code a lot easier to read. I use it even when I'm not using the Tidyverse. I will often use the pipe. I will note that in a very soon upcoming version of R 4.1, which should be released in the next few months or so, I think, they are going to incorporate the pipe into base R. It will no longer be a Tidyverse specific thing, and it will be a little bit different. It will look like this, a straight bar there, and then a greater than sign for the pipe, but it will work mostly in the same way. There are some minor differences in the implementation. Also, this pull variable is just basically a version of the $ here that works nicely with the pipe. That's all that is. Okay, so data wrangling. What is data wrangling? Data wrangling is when you have data and you want to do some sort of analysis with that data, but it is not yet ready for you to run the analysis on it. You need to get it into some sort of shape or format or cleaned usable values that you can use to run your model or analysis or whatever it is. That's all that data wrangling is. There are a couple of important tips that I would like you to follow when you're thinking about how to do data wrangling that have nothing to do with technical skills at all. One is to always look directly at your data so you know what it looks like. This is a very important part of data wrangling. You don't want to fly blind. Maybe once you've been doing it for 10 years, you have a really good idea of what your things do and you can fly a little bit blind, but I would not recommend doing it. So what do I mean by look directly at your data? I mean look directly at your data in a spreadsheet format. So let's say let's load up some data right here, my favorite, mtcars. I'm going to click on it, and it will show me all the values of all of my data in a nice spreadsheet format. Why is this good? Well, for one thing, I can look at it and immediately know what kinds of values are in there. I know, okay, it looks like VS can be 0 or 1. Looks like gear can be up to 4. It's counting variables. Looks like DRAT and weight and QSEC. These are all continuous numbers that have some decimal places in them. This is really important because as you're data cleaning, you need to know what the values are that you're working with before you can do any sort of operation to them. So you really want to be willing to look at your data. Next, once you've looked at your data, you want to think, what do I want my data to look like when I am done? Right? So you know what your analysis is going to be. Data wrangling is usually done in the service of some sort of analysis. You know what you want to do to that data, and you know that it's not ready yet. So you want to think, what do I want it to look like so that it will be ready, right? So if, for example, in this mtcars data, I think, okay, I want to run a regression, well, it's probably already in the format for that. I don't need to worry about it. But in a lot of other cases, you know, the data might not be ready, but I might want it to look like this, right? If I want to run a regression, I probably want the data to look like this, where I have a bunch of different columns. Each of those columns has some numeric data in it, and then I can just relate them to each other because they're, one row is a given observation of data that I can regress one variable on another. Once you know what it looks like to start with and how you want it to end up, you just got to think, how can I take the information from where it currently is and put it where I want it to be? So this is going to be the steps of moving data from one place to another. That's really what data wrangling is. For example, let's say that we happen to get this data set instead. We open it up, it looks like this, right? So in this data set, I've got all my variables that I might want to do on the in the rows here, and all of my observations in the columns. That's not what I want. Okay, well, here's what the data looks like. What do I want it to look like? I want it to look like this. Okay, how do I move the information from where it is to where I want it to be? In this case, that's pretty easy. I just want to flip the columns and rows. That's just a transpose, so I can just say, hey, t empty cars, and that will give me back what I want. All right. There we go. That's what I wanted. Okay. So, and every time you do an operation like this, that you take data from where it is and you put it where you want it to be, you always want to look at your data again to make sure that it actually did what you are doing. Data wrangling often is something that you do at the start of a project and then do not revisit, which means that if you make a mistake, A, it can be easy not to notice that you've made a mistake, and B, you probably won't catch it later until something has gone terribly wrong and you're like, that doesn't make any sense at all. So then you go back and you check it. And a lot of these functions are easy to get wrong in minor ways. So you want to make sure that you are indeed getting what you think that you're getting. So to make an example, we're right here where we have our data on our variables on our rows and the data on our columns. Okay, we know how we want to do it. We want to flip it. Okay, so let's go ahead and flip it. Let's say that I'm going to do like that, and then I say, oh wait, no, look, that doesn't work. I accidentally transposed it twice, so I'm back to where I started. But I wouldn't know that if I didn't check it, right? If I just took that command that I did and I said, okay, here's my fixed data. Great, there's my data wrangling done, and I start doing my analysis, it's going to be all wrong. I need to actually look at what I've done to notice that I've made a mistake. Looking at your data over and over and over again is the best advice that I can possibly offer you when it comes to data wrangling. Never assume that you got it right on the first try. I've helped a lot of people with data wrangling over the years. Usually when they have a problem, it is a lot more likely to be one of these problems, that they're not looking at their data enough or thinking about how to move data from where it is to where they want it to be, rather than any sort of technical skill that they're lacking. Lots of ways to look at your data, which I do recommend doing a lot. You can click on the data set like I just showed you. You can type view with a capital V on your data set. That will accomplish the same thing. There are also plenty of ways in R to get summary statistics tables or tables that describe the variables in the data. I tend to use the vtable package, largely because I wrote the vtable package. So the vtable of empty cars, right? It will show me the information about the data that I need. It will give me a bit of an idea of what's going on in there, what types of variables that I have, the values that they take, whether there's any missing data. Having missing data will sometimes affect the kinds of data wrangling you can do, and just a brief summary of the variables as well. Also in the empty cars, there's the sum table function, which will show you the distributions of your variables and what values they take if they're categorical, which can also be handy for in the same way that looking at the data set is. This can just sort of summarize it down for you. All right, so that is sort of our goal here with data wrangling. Now we are going to actually go into how we can do it. There are three main stages of data wrangling, and depending on which kind of data you're given, you might be able to skip some of them. But the first stage is going from records to data. Once you have your data, you can turn that into tidy data, which is where the Tidyverse got its name, but of course that is a broader idea than just the Tidyverse. And then once you have your tidy data, you can prepare it to be data for your analysis. So let's start with going from records to data. And so what do I mean by records? Records are with the actual raw data in the format that they originally arrived in. This can be anything. This could be it could be an API that you're going to use to download some data, right? Google Trends has some information on our marketing terms. Go get that data. You could be handed a giant PDF with pages and pages and pages of data that are not in a statistical package format or Excel format or anything like that. That's very common. Just today, I got somebody emailing me and saying, hey, I have this 12,000 page PDF. Can you turn it into data for me? And that's something that I'm going to be doing tonight. You could be getting scanned data, like scans of handwritten notes. That's some toughie. You could have a website. You may want to scrape a website in order to get your data, right? There's data out there that you need to turn into something that your computer can read and understand. When you're doing this, what I would recommend, first of all, do as little by hand as possible. Try to get as much automated in the process as possible. Again, look at the data a lot. And the problems that you're going to run into here are going to have a lot to do with formatting and telling the computer how to recognize the data. So for example, if you have a table in your PDF file, right? Here's your table, super easy. You can look at it and know exactly what your data is supposed to look like. And then you want to tell your computer to read in that data. And so it might get a little bit confused. Let's pull up a PDF actually. Let's just go ahead and pull up, oh, let's say this paper right here. Oop, didn't like that. So here's a PDF, right? You can tell that it's not text, right? It's an image. And so this might be some kind of data that you might be given that you would need to read in some way. So if we can go down and find a table, here's the table of data. How can we get it in, right? I can't just copy paste it. Sometimes copy paste works if you don't have that much data. But you might try to get something to read the text. Well, okay, how do you get it to recognize that going from this column to this column is a break in columns? It can't notice that there's just a big space here. You need to tell it how to recognize that. It goes from line to line. How do you tell it do this? This text right here takes up multiple columns. How do you get it to recognize that? So thinking, how can I tell the computer how to recognize where the data starts and stops is a big part of reading in data from records, especially not particularly well formatted records. And this applies even if it is already in textual format, right? If you were given this as an actual piece of text, you need to tell the computer to say, hey, look for, let's say, 5 or more spaces in a row, and that's how I know to jump from one column to the next. That's fairly common as well. So yeah, you want to tell your computer how you can spot where the actual data is. I'm not going a whole lot into the technical details on this, largely because there are so many different ways your records could come in and so many different tools that you could use that any one tool that I picked out to show you would not really cover enough use cases to be worth it. But these are the kinds of conceptual things that you need to think about when this is happening. You can, if you really have to, do hand-by-hand data entry. I recommend not avoiding that if possible, especially if the data is large, but even if the data is small, you're a lot more likely to make errors. Something that is a bit easier is if you just have a bunch of records that are already in computer format in some way. So if you just have a bunch of different files, this is fairly common. Let's say you're given a folder with 200 Excel files in it, right? And you're supposed to read them all in so you can start combining them all together. The way that you would do this in R is you'd use the list.files function. This will generate a vector of file name. So if you do list.files to, let's say, look for all Excel files, .xlsx, it would give you the list of all the Excel files that are in a given folder. Then you can take that vector of file names and read them in one at a time and then pop them all together, right? The way we're going to read them in one at a time is with the map function in a package called per. Then we can combine them all together with the bind rows function. Let's walk through how this works. So let's imagine that we have 200 monthly sales reports that are all in Excel files. We know that there are 2 cells of data that we want to bring in, and we want to read in each Excel file, pull those cells, and then combine together those two, or combine together each of the 200 reports into their own file. So first thing we're going to do, we're going to use the read Excel package, which reads in Excel files. And then we're going to use the per package, which is for iterating. It sort of takes the place of for loops. So the next thing we're going to do is we're going to use list files to get all of our reports. So what am I doing here? I've got list.files. I'm looking in the monthly reports folder. In that report, I want it to give me every file that has the word sales in its file name. And I want it to give me the full names, which will give me the full file path of those files so that I can read them in directly. Once I have this, I will have a vector of file names that I can then go through one by one to read in. So here's how I can do that. Muted myself. There we go. What I'm going to do is I'm going to create a function. I'm going to create my own function that's going to read in these files. I'm just going to call it process file. That's going to be a function. Writing functions is a good way to reduce some redundancy in your code and make it a little bit more robust. In it, I'm going to say, once you give me a file, or give me the data set that you just read in, pull out this cell of data, pull out that cell of data, and then give me back a tibble. Remember, the tibble is a data frame with those two variables. So I've got the sales value that I've pulled out here. I've got the employee of the month value that I've pulled out. And what I've gotten back from this function is a one-row data set. So then I can get my compiled data all together very simply. I've got 200 files. I'm going to read them all in 4 lines. So I'm going to take that file list that I had from before from list files. I'm going to pass that to map. Map will go through my list of files, and it will use this function on each of them. What is that function? That's the read Excel function, which will read in the Excel file. So now I've got, instead of having a list of 200 file names, I've got a list of 200 files, right? And I've got the data set of the Excel data in each of those files in 200 different places. I'm going to take those 200 different files, I'm going to pass them again to map, so it will go through each of those files to process them, to pull out the sales data, pull out the employee data, and then return that one-row data set. So then I've got 200 one-row data sets. I started with 200 file names, then I had 200 Excel sheets read in. Now I have 200 one-row data sets, and I'm going to bind them all together, which just takes those 200 data sets and sort of stacks them up on top of each other. Any questions at this point? That's sort of the end. That's as far as we're going to go into reading in records. This is the sparsest part of the workshop, just because there's so few specifics that I can really do it.
So would all the 200 Excel files, would all of those files need the sales column in order for it to work?
So yeah, so this function that I've written assumes that the sales data is always in the first column, or sorry, the first row, third column, and that the employee of the month is always in the 42nd row, second column. So this does require that all of the Excel files have the same structure. If they don't all have the same structure, then this function would need to have some way of searching for that data in the Excel sheet. So for example, it might do something like, locate where the word sales pops up and then look one cell over. And then look for where the words employee of the month pops up and then look one column over. And that is something that you want to do when you're reading in records, is to make sure that the formatting is consistent across all your files. And if it's not, that your code needs to be able to recognize that. I've certainly dealt with problems where I've had to read in, 800 Excel files, and then it turned out that they changed the structure of the Excel file slightly in June of last year, so that, I need to have 2 different functions, one for reading in the old files and one for reading in the new files, and then I can combine them. So being aware of where the structure changes is important for reading this stuff in.
Thank you.
Any other questions? All right, moving along. So now we have our data in R, and we need to turn it into tidy data. So first of all, what is tidy data? Data regularly is just anytime you have your record stored in some sort of structured format. So even those 200 Excel sheets that we started with, those were data, right? There was a structured format. There was one file for, let's say, each week or each month, and the data was structured inside of it so you could know where to look at. However, there are a lot of structures that you could store data in. It could be across a bunch of different tables, as in our 200 different Excel files. It could be in a spreadsheet where the variables are stored randomly, right? If you've ever done your own bookkeeping, then you probably have a spreadsheet where everything is just sort of wherever you happen to put it when you felt like it. Or it could be one table per observation, where each person has their own table in the data set. Now, these kinds of structures are really great for looking up values, which is why you see them a lot in business context. So for example, if you want to say, hey, I want to know, how much did I earn in the month of March last year? Well, then I'm going to pull up my March table. I'm going to look up the earnings row right there, and oh, look, that's where it is. That's how much I earned in that year. So it's really great for that. However, it's not good for doing analysis. It's really hard to run a regression, let's say, on 200 different Excel sheets, right? So what we're going to want to do is we're going to want to create some tidy data, which I've also linked a walkthrough here that goes a little bit more into detail, but I'm going to focus on some certain parts of it here. So first of all, what is tidy data? In tidy data, each variable that you have forms a column, each observation that you have forms a row, and each type of observational unit forms a table. What do I mean by observational unit? An observational unit is the mix of identifying variables that sort of identify a particular observation, which is not that much clearer. So let me take another run at that one. So variables in tidy data come in two different types. Okay, so one type is the identifying variables or the keys. These are the columns that you would use to try to locate a particular observation. So I mentioned, for example, I wanted to know, hey, what did I earn of March of last year? Well, then I might say, okay, I am one of the person that we're looking at is an identifying variable. So I want to look at my data, and I want to look at my data in last year. Okay, year is another one, and I want to look at my data in March. So March is another one. So I might have three columns in that data set. One telling me what person I'm looking at, one telling me what year I'm looking at, and one telling me what month I'm looking at. And the idea of these columns is if I wanted to look up a particular observation, these are the columns that would tell me what observation I'm looking at. All the other variables are measures or values. These are the actual data that we are interested in looking for. So in this table right here, right, we have a person column, we have a year column, we have a number of points that they've earned, and we have how much shrimp they've eaten that year. So in this data, we have the person and year columns. These are the identifying variables or the keys. If I want to know how much a particular person, how much shrimp a particular person ate in a particular year, I would say, okay, I'm going to look for Eleanor. I want to know how much she ate in 2017. I'm going to use these two columns to look up the data that I want. And then I can look into the values or the measures, the shrimp consumption variable, to tell me how much shrimp she ate. So when I say that each type of observational unit forms a table, what I mean is that if I have some data that varies at the person year level, I would have a person year table. And if I had some other data that only varied at the person level, I would have a different person level table, right? So the sort of level of the data determines what kind of table you have. That last one you can get a little bit mushy on. I tend to ignore it sometimes and just put everything in the most detailed table. But for example, you can imagine having a second table here that just had person and let's say told you what gender that person was, right? So you'd have a second table over here that had a person column and a gender column. And because gender varies at the person level rather than the person year level, for most people anyway, then you would have a second table that is on the person level. Okay, so that's what tidy data is. We want to make sure that we get one variable in each column, one observation in each row, and we want to think about what our keys or identifying variables are. And if that's not clear to you yet, it might be easier when you see what some non-tidy data looks like to see sort of what is not that. How are we doing on time? Okay. So here's an example of a common example of some non-tidy data. This is what's called a count table. You might often see this in a business context. What a count table is, it's got some categories along along the rows. It's got some other categories along the columns, and then it shows you the number of observations that you have in each of those sort of buckets. So here we have, let's see, 33 Buddhists in this data who earn $40,000 to $50,000 a year, right? So this is not tidy data. How do we know that this is not tidy data? Well, because we have religion is a variable that's in its own column. Good, right? But income is a variable, and income is spread across like 9 columns here, 10 different columns here, right? So instead of having one column for the income variable, we have 10 columns for the income variable. This is going to make it harder to work with the data because it's not tidy. We also want to have one observation per row. We certainly don't have that here, right? Here, this cell right here represents 137 people. All of the agnostics are on this row, right? Instead of having one row per agnostic, one row per atheist, one row per Buddhist, one row per Catholic, one per blah, 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 and so on, right? So clearly this is not tidy data. So here's another example of a count variable, sorry, not a count data, but here's a variable where the data is split across multiples. So here what we have is songs. We have some songs and their Billboard chart positions. So this Tupac song in 2000, in the first week of 2000, it was number 87 on the charts. And then in the next week, it was number 82. And then the next week, it was number 72. And then the next week, it was number 77, and so on, right? Why is this not tidy? Well, what are our identifying variables? What are our key variables? Well, we might want to know information about the song, right? So we got the artist, the track, maybe the date that it started, maybe the date that the song was released. And then we might also want to know, okay, well, in what week is it a given position, right? So that week should be also a key variable, should also be an identifying variable, but the week is split across a bunch of different columns, right? Then the actual value that we might want to look up is the position, the chart position of that song in that week, which should be a single column by itself, but we don't have a chart position variable here. We have a bunch of week variables, and we got the chart position stored in each of them in kind of a weird way. So this is what non-tidy data looks like. So what can we do to turn it into tidy data? There's a couple of big tools that tend to fix most problems along this stage. The first big tool is the pivot. What a pivot does is it takes a single row with a bunch of columns and turns it into a bunch of rows with one column, right? So like we have here, we have a bunch of columns, and we're going to turn into one column that goes across a bunch of rows. It uses the identifying variables or keys to make sure that everything is lined up, so that we're going to have Tupac with Baby Don't Cry that entered in this week, and we're going to have however many rows of data we have here. Let's say, I think there's 52 week variables here, something like that. So we're going to have 52 rows, all of which have Tupac, Baby Don't Cry, 2000, Tupac, Baby Don't Cry, 2000, Tupac, Baby Don't Cry, 2000, blah, 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 52 times. One for each of the weeks that we want to store. Then we're going to have a variable for the week. Week 1, week 2, week 3, week 4, week 5, week 6. And then we're going to have the actual chart position, 87, 82, 72, 77, blah, 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 right? So it's going to go all the way down like that. That's what the pivot is going to do for us. This is also referred to as going from wide data to long data. Wide data is data where you have a single variable sort of scrunched up into a bunch of columns. And long data is where you have one row per observation. You can also go the other direction from long to wide. We'll talk about that in a bit. I will point out, we're about to go through the syntax for doing a pivot in the Tidyverse. Something to note is that in pretty much every statistics package, pivot functions are notoriously fiddly and hard to get right. I've mentioned before, you always want to look at your data before and after you do everything. This is like triply true when it comes to pivots, because you're very, very likely to get it wrong. So check what it looks like after you've done it to make sure that it looks like you think it's supposed to look. So let's do a pivot. So we looked at the data. We thought about how we want the data to look. We want it to be one row per artist, track, and week. And then the chart position is going to be in its value column over here. We can carry information from where we want it, which is across all these columns, into all these rows with a pivot, because that's what a pivot does. It goes from a bunch of columns to a bunch of rows. Then we're going to look at our result. So in the Tidyverse, the pivot functions are pivot longer to go from wide to long, and also pivot wider to go from long to wide. Here we want wide to long, so we're going to use pivot longer. Specifically, this is in the tidyr package, which is a part of the Tidyverse. The arguments that pivot longer is going to take, it's going to need the data that we're working with, of course. It's going to need the calls, which is the columns that we're going to want to pivot. So everything that is currently in wide format that we want to take long, so that's the week variable here. We want that to be in the calls. Names too is what it's going to be named, what name it's going to give the new variable. So we have week 1, week 2, week 3, week 5, right? So we need to store the values 1, 2, 3, 4, 5. What do we want to name that variable? So we know which week we're in. Here we're going to call that week. And then values to is going to be the values, what the actual chart position is. So we had 87, 82, 77, whatever. When we turn that on its head, what do we want that variable to be called? That's going to be chart position. There are, of course, many other options. You can look at the help file. So we're going to take our Billboard data. We're going to pivot it. Notice that I don't have to put the data argument in here because I already used the pipe to send it to pivot. So that was the first argument. So the columns that I'm going to give it, I'm going to use a starts with function. So this is like what's called a tidy select function. It's part of the Tidyverse. It helps you select many variables at once. So if we go back here, we have a bunch of variables that we need to specify. We need to say week 1 and week 2 and week 3 and week 4 and week 5. That would take forever if we actually had to type it all out. Thankfully, we don't. Instead, we can just say, where did we lose it? There we go. Give me every variable that starts with the letters WK, right? Which is what we had. It's going to pivot all of those. We're going to call the new week variable week. We're going to strip out the WK that it starts with. So if I had left this part out, the week variable here would say WK1, WK2, WK3, because those are literally the names of the columns that we had. But I want to strip out the WK and just leave the number. So I'm going to take out this prefix here. I'm going to do values2. That's the name of the chart position variable. And then I'm going to choose to drop everything that's missing. So what do I mean by that? If we go back here, notice that if a song was only in the charts for a few weeks, it then is no longer, this song right here by Together doesn't have week 4, week 5, week 6, week 7. And so if I turn that each into its own row, this blank value is going to have its own row all to itself. Do I want to keep that or not? Well, if I don't want to keep it, I can just drop it with the values drop NA option right here, and we get this nicely formatted long form tidy data set, right? So here's the key variables: artist, track, date that it entered, and then the week. And then we have the chart position, which is the actual value that we would look for there. Another tool that we can use pivots for, in this case, we're going to look at pivot wider, is when we have variables that are stored as rows. This is another one that you see very commonly in business data, especially in accounting data. It might be the most common, the most natural form to store, let's say, a tax form in Excel, right? So in this case, what we have is we have our variables on the x-axis, or on the on the rows here, and then we have different columns with the values in them. So here we have the person that we can fill in their name, we got their income, we have their deductible, we have their adjusted gross income, right? We want to turn this tidy. We want each variable to be in its own column. And each value to be in its own, or each observation to be in its own row. So here, really, we have a 1-row data set that has been sort of mangled into a 4-row data set, because there's only one person in here, and that's James, so we want that person to be in their own row. Now, I showed before how you could do this with a transpose by just flipping it, but that would not actually do what we want here, because if we transpose this data set right here, we would have 2 rows. This would be the first row over here, person, income, deductible, AGI. This would be the second row, James, number, blah, 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 right? We want to have 1 row where these are the variable names. So we're going to use pivot wider. So pivot wider, again, goes from long format to wide. It needs to know the data. It needs to know the ID columns, right? So again, it needs those key variables so that it knows what to hold on to when it flips. It needs the names from. So what is the column that has the new variable names? So here we want these to be the variable names, right? So that's what we're going to give it. We're going to say that tax form row gives us the names of the variables that we want. And then the values come from this one right here, the value column. Of course, lots of other options. So we can do that here. So we take our tax data, we send it to pivot wider, say that the names are coming from tax form row, the values are coming from the value row, and it does it for me. Notice that I left out the ID columns because there's not really because there's only one observation here. There's no ID column. Excuse me. But if I had, let's say, another set down below here with a different person in it, I might have person 1, person 2, and then I would need to give it an ID column. All right, so then we have our 1-row data set that is properly named. Something to note here is that these are all character variables. They're all strings. Why is that? Because when I gave it, this data, this column right here has a string in it, has the name, right? And so so this column is all strings. And so when I flip it, they're going to still be strings. And so I'm going to need to turn them to numbers by a little bit later. I'm going to need to turn them to numbers if I want to treat them as numbers, which I'll do a little bit later. You can, again, use bind rows if you have multiples of these. If you have a bunch of different tax forms that are all sort of in this format, you could use pivot wider to turn them all into properly formatted tidy data sets, and then bind rows to sort of stack them on top of each other. So I took another data set with the exact same format, did pivot wider on that one, and then I used bind rows to sort of stack them all together. So now I have multiple people in one place. Any questions at this point?
I've got a quick question for you. I recently had an experience of having some stuff set up through R of checking through some data, and I think it was using dplyr and some tidier stuff. Have you noticed any difference in R's ability to chug through it when it's using 32-bit versus 64-bit version of R or RStudio? I think that's the issue I was running into, was someone else trying to run my code, but they didn't have 64-bit, so they were tapping out R, but I don't know if you've experienced that before.
I don't think, I'm not sure, I'm not familiar with it being performance issue related. It could well be that based on the type of variables that you're looking at or the size of the data, it might have to chunk things in different ways on the back end. I wouldn't know. I just always use 64, so I never really run into that problem, but it's possible, yeah.
Thanks. Yeah, I think it's something for me to bug IT about to fix this person's setup.
Fun.
Could you repeat the difference in application for pivot longer versus pivot wider just one more time to make sure I have it right?
So pivot longer is when you have wide data and you want to go long. So if you have the same value, the same variable stored in multiple columns, then you can turn that into one column with pivot longer. Pivot wider is when you want to go the other direction. So if you have multiple variables in the same column, you can turn them into multiple variables with pivot wider.
Thank you.
I have a question. So if we're working with multiple data sets that, let's say, need to be, pivoted or unpivoted in this way, would you run into any issues if you had to bring all of those data sets together in R and do that and then bring in and then put them together? I mean, I'm thinking about sometimes some of the issues I run into with things being sluggish when I have to transform data a ton. So, is it better to, if you have to, again, bring in a lot of different files together, maybe into one data set, to do those separately and then bring those clean data sets in? Or
there is an issue where as the size of the object you're working with gets bigger and bigger and bigger, it's going to be slower to work with because the way that R works, it will need to modify the whole object and sort of rewrite it in data every time you update something. And so if you're bringing together a bunch of different files, it's generally a good idea to do as much processing on them as you can before you bring them together, which doesn't really take much more coding if you just do it in a function and you use map like we did before.
Okay, thank you.
I will also say that as you get to really, really big data files, Tidyverse ceases to be the best tool for the job. And then you might want to switch to something like data.table, which we'll talk about in the next workshop.
Okay, thank you.
Okay, so with all that in mind, let's talk about merging data. This is something that you're going to have to do a lot when you are working with data wrangling. So merging data is when you want to link two data sets together based on shared keys. We've been talking about keys and identifying variables a lot. There's a good reason for that, because you always want to be thinking about what are the identifying variables and keys of this data set. And you're going to need that information if you want to link two data sets together. So here's an example. So let's say we have two data sets here. One has the variables person, year, and income, and the other one has person and birthplace, sort of like I alluded to before, linking up shrimp and gender. So here we have person, we have Ramesh, we have Whitney, and we have David in 2 different years, 2014 and 2015. These are our key variables. These are identifying variables. And this shows me the income that that person made in that year. Then we have this other data set, which has the birthplace of that person. So we have one column for person, one column for birthplace. Obviously, this does not vary by year. So we only need 1 row per person rather than 1 row per year. But let's say that we want to do something where we look at the relationship between birthplace and income, right? Well, we need both of these to be in the same data set. We can do that with a merge. So in dplyr, which is a part of the Tidyverse, the join family of functions is how you would typically do a merge. There are many different join functions. The different varieties of join function mostly just determine what you do with rows that you don't find a match for, which actually I'll come back to that in a second. Realizing this slide probably should have come later, but let's see just how we can use a join function. I'll be using left join, and I'll talk about what that means in a second. So the left join function takes 2 data sets You can give it the key variables that you want to, that you're going to be able to say they link the data sets together, and it will then join them together. You can actually often get away without specifying this. It will figure it out for you. That's good to know. But what do we got here? So I'm joining the person year data to the person data by person. And so what it's doing is it's looking for where there's a match between the two data sets, and it is filling things in. So here's our original data. These three columns over here on the left, these are the original data that we started with, right? And then we wanted to bring in the birthplace data. So what it did is it went row by row. It said, okay, here's Ramesh in 2014, and I'm looking at person here as my key variable. So here's Ramesh in 2014. That links up to Ramesh who lives in Crawley, or is born in Crawley. So boom, Ramesh gets Crawley. Here's the next row, also Ramesh. Okay, well, where's Ramesh in this data set? Oh, born in Crawley. Okay, let me fill in Crawley. Okay, here's Whitney. We're looking at Whitney. Where's Whitney in this data set? Oh, Washington, D.C. So I'm going to fill in Washington, D.C. Same thing on the next row, Washington, D.C. How about David? Well, if I look back here, there's no David. David's not on this table. So David gets nothing. Okay, so what merging does is it takes your key variables that you are merging, that are shared across the two data sets. It looks for where they match, and then it fills in the values from one data set, brings it into the other based on that match. Right? So we had a match on name here, so we brought in the birthplace of the matching name. So that's how merging works in general. What about those different merge functions that I talked about? Those basically determine what happens when you don't have a match. Okay? So in this case, we have David, who does not appear in the person data set. So left join is going to keep all the matches, or keep all the, all right, so if you have a, sorry, if you have a row that does not have a match, left join will keep that row if it's in the first data set, the left one, but not if it's in the right data set, the second one. So we had David was in person year data, but not in person data. So he did not find a match, but he was in the first data set, right? The left data set. And so we kept David, even though he couldn't find a match. What if we use right join instead? If we use right join, then we're going to keep all the rows that did not find a match if they're in the right data set, the second data set, but not if they're in the first one, right? So David was in the first one, but not in the second one, didn't find a match, so he gets dropped because he's not in the right data set. So David does not end up in here. There are many different versions besides left and right. There's full join, which keeps you whether you find a match or not. So it keeps you whether you're from the right or the left without a match. Inner join keeps neither of the non-matches. Anti-join keeps just the non-matches, right? So you have a bit of flexibility there in terms of which ones you keep. Something to point out about merging is that you want to be very sure that you know what your key variables are. Because if you are wrong about that, if there are duplicates of your key variables, then you're going to have some problems. In general, there should be only one row in your data set for each combination of your key variables, right? Let's go back up here. Our key variables are Ramesh and year. And so if we had two different rows that had the same value of person and year, we'd have a problem, right? What if we had a second row in here that was Ramesh 2014 and 70,000 in income? That would tell us that Ramesh earned both $81,000 and $70,000 in the same year. That doesn't make any sense, right? That would tell us that, in fact, person and year are not our key variables, right? So we don't want to have duplicates of the combinations of our key variables. It's fine that Ramesh is on here twice because person is not our key variable. Person and year are our key variables, right? And so it's fine that Ramesh is on here twice as long as Ramesh 2014 is not on here twice, right? And we certainly wouldn't want Ramesh on here twice for birthplace. Can't have two different birthplaces. So what happens if we're wrong? What happens if we think that we have a certain key, but we are wrong about that? So let's make some fake data and see what happens. So here we have some data where in tibble A, we think that our key is name, but we have, we think that our key is name and year. And we are right about that. There's no duplicates across name and year. We have A twice, but that's at two different years, right? So fine. So our key variables for data set A are name and year. Good to go. How about B? On B, we think that we have a key of name, that name should be our key variable, but we have duplicates. We have 2 A's, we have 2 C's. That's a problem. So we think that our key that the match across the two is name. We think that name is both a key variable over here and a key variable over here, but in fact, name is not a key variable over here because we have duplicates. When this happens, it will still let you do the merge, but it will do something weird where it creates all the different combinations of the different key matches that you could have. So we have A over here on both 2014 and 2015. So we're going to get 4 different rows for A. We're going to have A 2014, A up, A 2014, A down, and A 2015, A up, and A 2015, A down, right? All the different combinations you could have in here, which usually is not what you want, okay? So that's why it's important to be sure of what your key variables actually are before you do a merge. There are ways you can check whether your key variables are what you think they are. We just start with our data set. We select what we think our key variables are. We check if there's any duplications. What duplicated will give us is a set of indicators of whether a particular observation is duplicated. And then the max will tell us whether anything is duplicated. So if you run this on your data set and what you think your key variables are, it will tell you true if there are duplicates and false if there are not. So then if there are duplicates, you can figure out how you want to proceed. Maybe you can put in a new key variable to identify it further. Maybe you can drop some of the duplicates. Maybe some of them are wrong or errors. Or maybe you do want those crosses. You can also use the function safe join in the PM dplyr package. Safe join basically just runs the join functions, but it forces you to tell it what you think your key variables are and what you think is going to happen. And so if that's true, then you're good to go. And if it's not, then it will give you an error rather than letting you do the merge anyway. It also has an inexact join function, which allows you to do merges on inexact joins. So let's say that over here you have name and year, and over here you just have name and let's say a different type of year, and you want to merge them together. But there's gaps in the years, so you want to merge like the most recent year. Inexact join will help you do that. For things like dates or numbers. If you want to join on text that does not match exactly, you can use the fuzzy join package as well. All right, that is all we have for turning data into tidy data. Before we move on to the next section, are there any questions?
I have a question about checking duplicates on your keys.
Yep.
So I saw in that slide, you put 1 variable in there. Does that only take 1 variable?
No, you can put multiples in here. So you can do person, comma, year, for example.
Okay, thank you.
I had a question on that too, in the other slide where we had A and B defined objects. So on A, did you say that we were thinking that the key for A is name and year?
Correct.
And then why wouldn't we assume that the key for B is name and characteristic?
That's a good point. So I guess in this, we're not assuming that it is. I'm telling you that characteristic is the value that we're looking up, and name is the key. Yeah. Okay. Yeah.
Fair enough.
I mean, you could look at a data set and say that pretty much anything is the key. Like I could look at this here and say, okay, well, look at MT cars and say, okay, MPG, that's the key here. I can uniquely identify all the rows by the different miles per gallon. And that's actually a value that we want to look up rather than actually being identifying it. So it's more about how you're planning to use the data, what the keys are, rather than necessarily what's in the data.
Okay, thank you.
Any other questions?
I do have one question. One time I found the data have like multiple columns, like 2 levels, 3 levels column. How do you like lower the level to make them a good database?
So when you say levels per column, do you mean like there are multi-value objects in them, or like there are like 1, 2, 3, 4, and you want it to just be 1, 2?
It's like hierarchical index. So it's like they have a column name, but under the column name, they have another column name.
Ah, got it. Yes, that is very common. That will often be something that you can deal with on your data reading function. So let's see here. So let's take, for example, usually there's like a skip. So taking this one, for example, Let's see here. Skip. There's a skip option in read Excel, and most other file reading functions will have a skip option like read CSV or whatever. And what this does is it skips a row. And so you can have it skip, like, so let's say that first row that has that other column on it. And then so it ignores that. And then you just have one row of variable names.
Okay, thank you.
Any other questions? All right, so we have our tidy data, and we are going to now turn it into the kind of data that we can use in our analysis. What do we need to do? So we need to take the data that is in the structure that we want it. It's sort of in a nice rectangular format with one column per variable and one row per observation. But often we need to do some sort of other manipulation to that data set to get it where we want it to be. This is going to be mostly a dplyr task, which again, dplyr is a part of the Tidyverse. So if you load in the Tidyverse, you'll get the pipe, you'll get tidyr, which we've been using for like the pivots, and you'll get dplyr. So what dplyr is it is a small set of verbs that are very flexible to use in terms of how they can be used for data cleaning manipulation. You can do most forms of data cleaning at this stage, from tidy data to prepared data, using these using a very small set of verbs. These verbs borrow a lot from SQL. And so if you use SQL, you will recognize a lot of the sort of concepts here. And once you learn dplyr, it will be a lot easier to jump then to SQL. So the main verbs that we're going to be interested in are filter, select, arrange, mutate, group by, and summarize. And I'll talk about each one of those in a bit more detail. There are some other important functions. One is pull, which we already covered. Pull just takes a variable out of a data set in a pipe-friendly way, and case when. There's also, of course, the available dplyr cheat sheet that you can find online that will be very handy. When I was first learning dplyr, I just printed it out, I taped it up above my office, and I looked at it all the time. So let's start with our first verb, which is filter. Filter limits the data to observations that fulfill a certain logical condition. It picks certain rows out of the data set. And so when you are done with your filter, you will have fewer rows than you started with. So for example, what I mean by a logical condition, let's say income is above 100,000. If income is above 100,000 is either true or false for you. If your income is above 100,000, then it's true. If it's not above 100,000, then it is false. And so we can use filter to just return the rows of data that have true for that condition that we are checking. So we can take our data, Whitney, David, and Ramesh, and join it to that person data that we already had. So this is the joining operation we already did. And then I'm going to filter it to just give me the people who earn more than $100,000 a year, which are Whitney and David, right? This requires us to use a logical condition. We need to feed logical conditions into filter to tell it which rows to give us back. We want all the rows for which the logical condition is true. And a lot of programming is based on writing logical conditions. You want to be good at it. You will get better at it through practice if you're not good at it yet. But to do any sort of coding thing, you're going to need to understand how logical conditions work. In our logical conditions, either evaluate to true or false, which also correspond to 1 and 0 if you try to do calculations with them. By the way, there's also an if-else function that you might have learned when you were learning R. It's rarely what you want. And something I see people coding up a lot of the time for some reason is if-else condition true, false. This is redundant. The condition by itself will return true if it's true and false if it's false anyway. So this is just a waste of typing. So some tips for constructing logical conditions. If you're checking two numbers, right? A is greater than B. This asks, is A greater than B? If it is, true. Is income greater than 100,000? Right? Is A greater than or equal to B? Is it less than B? Less than or equal to B? The double equal sign checks for equality. So you might be familiar with using an equal sign to assign variables in R or other programming languages. A single equal sign usually means assign this value. So A equals 1, right, would say, hey, take this variable A, make it equal to 1, right? Whereas A double equals 1 asks, is A equal to 1? An exclamation point and then equals asks if it's not equal, right? Is A not equal to 1? No, because it is equal to 1. Another one people tend to skip past is the in function, which is pretty handy. If you want to check if something takes one of a set of values, you can use the in function or in command, which is %in%. This checks whether A is is equal to any of these things, right? So not just one thing, but any of these things. So I could say is A in any of the numbers from 2 to 5? No, because it's 1. Is it in any of the numbers from 1 to 5? Yes, because it's 1, right? So these are some nice tips for constructing logical conditions. There are, of course, many, many other ways you can do so. If you want to invert a logical condition, you can just put some parentheses around it and then put a exclamation point in front of it. So for example, if I want to check if 2 plus 2 is equal to 4, I do 2 plus 2 equals 4. That's true. If I surround this in parentheses and then put an exclamation mark in front of it, this is saying, is 2 plus 2 equal to 4? Yes, true. And then, is true not true? No. So then we're going to reverse it to make it false. You can also chain together multiple conditions. And is shorthand for and. This pipe here, confusingly the same name as the other pipe, but not the same thing, is or. Be careful with parentheses if you're going to combine a bunch of different logical conditions. And in filter, you can skip the and just use commas. So I can say, is A equal to 1 and A less than 5? Yes, both of those things are true. So, good to go. Is it greater than 5? No, there's only one of those things is true. Is A equal to 1, or is it greater than 5? Yes, because A is equal to 1. So this value is true or false, and true is true. So good to go.
Professor, can I hop in with a quick tip too? If you want to do like there's the in operator, you can create your own not in operator, and I just threw in the chat how to define that. So if you run that code that I put in the chat, then you can use a not in operator pretty usefully.
Handy. Yeah, that is a good tip. All right, so that's filter. So filter will pick us back some rows. Select does the opposite, or not the opposite. Select goes on the other axis. It gives us back some of the columns. It picks columns. You can do this by either name or column number. You can also use a minus sign to unpick some columns. So let's say we had a data set that had the columns person, year, and income in it. We could pick just the person and year variables in a couple of different ways. I could say, hey, person, year data, pass that to select, give me back person and year. And there was the question earlier of can I use select to get more than one variable? Here's one way you can do it. I could say, instead of person, year, I want the first 2 columns, which happen to be person and year. I could do select 1 to 2. I could say, give me back all the columns except for income, right? And that would work as well. So all 3 of these are ways of using select to narrow down the columns that you have. You can actively pick the columns you want by name. You can actively pick the columns you want by their number, by the index position that they have, the first column, the second column, the third column, or you can pick which columns you do not want. This one can come in handy a lot, especially if you have a data set with lots and lots of columns in it. Often you will want to just do a few, or you'll want to get rid of a few and keep a lot of them. You don't want to type all of them out. Something else, you can also use those tidy select things that I mentioned before. So for example, let's say I want to, for some weird reason, get rid of all the variables that start with D from MT cars. I can do MT cars, select, minus, because I want to get rid of these columns, starts with D, right? And so I've gotten rid of drag and what was the other one? Disp, right? So starts with, there's also ends with, there's a bunch of other ones that are in there. If you help tidy select, it will show you all of the different variants that are, or at least there's a link to all the different ones that are there. All right, select pretty straightforward. Arrange is also pretty straightforward. It sorts the data. That's it. If you give it the column names and put columns between them, it will sort the data by those columns. Arrange is often a good idea to apply before you save your data because it will make your data easier to look through next time that you open it back up. There are also some data manipulation tricks we'll talk about in a bit that rely on where the data is in order. I should have had the code visible there, but let's do it in here. So let's say we have empty cars. We're going to arrange. Let's order it first by the number of cylinders, and then let's do it from highest mile per gallon to lowest. I'm going to use minus to sort in the opposite direction. So it's highest to lowest instead of lowest to highest. And so you can see here that we have cylinders, goes 4, 5, 6. It does all the 4s, all the 5s, all the 6s first before it considers miles per gallon because we have cylinders first. Then within each of these cylinders values, it goes highest miles per gallon to lowest, got 33 all the way down to 21, and then et cetera. That's how we can sort our data. Mutate. Mutate assigns columns or variables. So you can create variables with it or overwrite old variables with it. There's also the very similar command transmute, which is basically exactly like mutate, except if you don't specify a variable in it, it will get dropped. So it's sort of a combination of mutate and select. So you can assign multiple variables in the same mutate. You just separate them by commas. So for example, let's say we take our person year data. I want to create a next year variable, which tells us what the year after this one will be, which is just a year plus 1. And then I want to do an indicator variable, true and false. Is your income above 100,000? I did both of them in the same mutate. You can see here. I just put a comma between them. Now I've got 2 new columns on my data, right? Next year, which is year plus 1, and then above 100K, which is false because this one's below, and then true because this one's above. Notice something, by the way, in all of these things with dplyr, if you haven't been using the Tidyverse and you're used to, like, let's say base R, you would have had to do something like person year data $ next year equals person year data $ year plus 1. Person year data $ above 100K equals person year data income is greater than 100,000, right? So one nice thing about dplyr is you don't need to refer back to the name of the data set over and over and over and over again. It lets you skip that. So mutate, if you've ever used the Tidyverse before, you're familiar with mutate. There are a couple of handy tips for working with mutate. One is the case when function, which comes up a lot, especially when you're taking tidy data and turning it into something that you can analyze. What case when is it is sort of like if else, in that it checks a condition and it returns one value if it's true and another value if it's false. Except that case when does it for a whole list of if conditions in a row. You provide it with a series of if tilde then conditions. You separate them by commas. It will go through those one by one and give each observation the first one that applies to it. So let's see what this looks like. So let's say they want to create an income bracket variable, right? So I have your income, but I want to sort of separate it into brackets. So what can I do? I can mutate to create a new variable called income bracket. Good. And then I will create that variable using case when. Inside of case when, I will say, I will first check whether your income is below 50,000. If it is, I will tilde, say that you're going to be the under 50K category. Then comma to go to the next condition. The next condition I'm going to check, are you above 50,000 and also below 100,000? If that's true, I'm going to assign you to the 50 to 100,000 range. A little tip, by the way, this part right here is actually unnecessary, because if you're seeing this condition at all, I already know that you're above 50,000, because if you were below 50,000, I would have caught you here and you would have stopped. But I've included it here for clarity. So if this does not apply to you, then you go to the next one. Are you above 100,000 but below 120,000? Well, then you're going to get the 100 to 120,000 category. And if that doesn't apply to you either, you're going to go to the last one. For this one, I'm just going to say true, which means apply this to everybody who hasn't been covered yet, right? Everybody who's still in the game at this point, I'm going to say you're true, you get this category. I'm going to call you the above 120K category. And we can see how this works, right? So Ramesh is 81,000. So he looks at this and says, am I here? No. Am I here? Yes. So I'm going to get the 50 to 100,000, and then it stops. Whitney is 131,000. So is it here? No. Is it here? No, because I'm above 100,000. Is it here? No. So I'm going to keep going. Is it here? Yes. If I'm here, then I'm definitely getting above 120,000. So I get that value here. David does the same thing. He's 100,000. So he stops at this point here. That's how we can use case when to sort of chunk up a variable and sort of do conditional calculations. In this case that I just used it in, I gave values to fill in. It doesn't have to be, it could be calculations. So let's say, for example, that I have, I want to adjust for inflation, right? So one thing I can do to adjust for inflation is say, well, okay, I want to take your income and I want to multiply it by the different inflation factor, but that inflation factor is going to be different depending on what year it is, right? And so what I can do is I can say, okay, if you are in 2014, take your income, multiply it by the 2014 inflation factor. If you're in 2015, well, then just keep your income as it is. And now I'll have dollars in 2015 dollars. You can also use case when to change the values of just some of the observations, which is handy, especially when you're cleaning very raw data. A lot of the time, raw data will just have errors in it that you need to fix, but you only need to fix like that one row. Excel is very good at that. R is not as good at that, or at least dplyr is not as good at that. But you can use case when to do it. So let's say, for example, we got some new information in, and one of David's income values was wrong. We just needed to fix it. Or perhaps we found that everybody else's income was in dollars, but David's was in pounds. So we need to multiply all of his income by 1.34 to convert it into dollars. So I can use case when to say, okay, if you're David, multiply your income by 1.34, right? And use that to replace income. If you're not David, then just stick with what you had before. Yeah, so that's what we can use case when for. We can use it to chunk up a variable. We can use it to reassign values based on a function, but different functions for different rows. Or we can use it to just fix a couple of observations at a time. One thing to notice, or one thing to point out that can be kind of aggravating with case when is that it's very, very picky about variable types. And that's usually not a problem. It will shout at you if you try to assign, you know, a number for some of the columns and a string for some of the others, but that's pretty reasonable. However, it will also shout at you if you are trying to give it different kinds of missing values. What do I mean by that? In R, there are different kinds of missing values for different kinds of variables. So for example, I can have NA, which is, and we can ask, well, what kind of variable is NA? It's a logical, it's a true false variable. That's weird, right? But that's just because the default missing value is a logical for some reason. Now, if you're working in base R or many parts of dplyr and you give it an NA, it will just automatically convert it to whatever type you want it to be. So for example, if I do, let's say 1, 2, 3, 4 NA, right? And I ask, well, what's the class of fourth element here? It has converted it to a numeric missing value, right? Just automatically. Case when will not do that for you. It will shout at you. For example, let's take empty cars. And then let's say empty cars. And then let's mutate. Let's change our disp value. Case when I'm going to change, if you have 4 cylinders, I'm going to make your disp missing. If cylinders equals 4, then we're going to make your disp, we're going to make that disp equal to NA. And then for everybody else, we're just going to keep it as it was. This should shout at me. Yeah, it doesn't like it. Why doesn't it like it? Because I've given it the wrong type of missing value. This is a logical missing value, so it thinks that I'm trying to create a variable that is sometimes logical, a true false, and sometimes numeric. Doesn't like that. So to fix this, I need to give it the same type of missing variable, or a value that is the other variables. So this is a numeric variable, so I need to give it a numeric missing value. So I'm going to give it NA underscore real. Now it likes it, right? So same thing if I'm working with, say, a string variable, I need to give it NA. There's NA. You do NA underscore, you can see all the different kinds of NAs. There's NA character for string variables. If you ever work with complex data or complex numbers for some reason, I guess there's that. There's integers, which that one really gets me, because sometimes you have a variable that starts as an integer and you want it to turn into a real, and it will get angry at you. Anyway, that's something to keep in mind. If you get a weird error in case when, that sometimes is the issue. Okay, moving along from case when and mutate, we have group by. Group by is magical. I honestly, so I'm an economist. I was trained in economics. Economists tend to use Stata first and foremost. At least academic economists do. And so that was what I was trained in, was Stata, which is a different program. And for a long time, I hated R. I did not want to use R. I used it for a couple of things. And I just didn't get it, really, mostly because I didn't like how base R did data manipulation. And it was really when I found dplyr, and in particular group by, that I was like, oh, I get it now. I get what the point is. And since then, I've become more of an R person. So what group by does, it takes your data set and it turns it into a grouped data set. It then, once you have grouped data, the calculations that you do on your data will go group by group, okay? And so this can be really handy, especially when you're then gonna say do a mutate or a summarize or even an arrange, where you want it to do something within different groups. So let's say for your mutate, you wanna get the average value within person, right? You can do that with group by followed by mutate. You say group by person and then mutate, get the mean of income. It won't calculate the mean of income for everybody. It will just calculate the mean of income for that person. So let's see that in action here. So we take person your data, we group it by person. Now we have grouped data. It is sort of internally split our data into multiple different data sets depending on which person you are. So remember we had Ramesh, Whitney, and David. In its mind, it has the Ramesh data set up here, the Whitney data set down here, and the David data set down here, and it will treat them as separate entities to a certain extent. And then once you're done calculating on it, it will pop them all back together. So we're going to take this grouped data, and we're going to calculate income relative to mean. So we're going to take the income, and we're going to subtract out the average income that that person earns, right? So for Ramesh, we're going to take the average income, average of 81,314, average and 82,115. Take the average of that, subtract that out. So we can see that in 2014, Ramesh earned $420 less than average, and in 2015, he earned $420 more than average. Whitney earned $49.85 less in 2014 and $49.85 more in 2015, and so on. So you can see that it did this average calculation within person, so that each person is then average. If we added this column up, we get 0, because everyone's relative to their own mean. So this is very handy for mutate, any sort of variable creation that it relies on information about the group and not just that particular row. This is one reason why we want to use tidy data, by the way. It's really hard to use wide data to do these sorts of grouped calculations. Summarize, we'll talk about in a second, but takes your grouped data and it gives you back a data set that only has one row per group. So if you want to change the observation level, change the key level of your data set, you can use group by and summarize. There's also a function that I'm not going to go into deeply called group map, which lets you do all sorts of fancy functions and whatever you want with your grouped data. So you can pass it a whole function and just have it do all kinds of crazy stuff to your split up data sets, and then returns them back to you as one whole data set. So group by, if you group some data, it will maintain that grouping structure until you give it a different grouping structure with another group by, or you can use ungroup on it to return it to being ungrouped data, or you can summarize it, which, like I said, is going to collapse it down to being one row per group, and it will also remove one of the groups in the grouping data. This can be very useful in preparing data for a bunch of reasons. So one reason is we want to know where information is and think about where we can move it to where we want it to be, right? So group by can be very useful for moving information from one row to another. For example, let's say that we have long form data, right? And so we have, let's go back to that Billboard chart data. And I want to say, okay, this song in this week had this chart position. This song in the next week had that chart position. In the next week had this chart position, da, 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 da. How would I know if in a given week it is at a higher or lower position than it started at? How can I do that? Well, it's really hard to do with that long data, because I need to take this row down here that's this week's chart position. I want to compare it to the first chart position that it entered as, right? How do I make that comparison when it's across different rows of the same column? How do I know what row to refer to? Well, I can use group by. If I group by the song, well, now I'm using this data set of just this song all here by itself. And I can say, hey, refer back to the first row of that data set. Well, now I know exactly where to compare to, right? So it's going to help me figure out where that information is so that I can compare it. And I'll give an example of that in a second. Summarize can also let us change the observation level, as I mentioned, which I'll talk about more in a second. There's some handy functions that become relevant when you're using group by. One is the n function. This gives you the number of rows in each group. So in that chart position data, if I wanted to know how many weeks is this song in the charts at all, I could use mutate to create number of weeks in chart equals n parentheses. And it would tell me how many rows of data I have for that song, which is how many weeks that song is in the charts. Row number will tell me the position, the row position of that particular row in that data set, in that section, in that group. So I mentioned here's this song in this week. I could use the row number, and it would tell me, is this the first week that it was in the charts? Is it the second week that it's in the charts? Is it the third? In that particular case, we already had a variable that was telling us that, but in many cases, we might want to get that information new. Let's talk about using group by with summarize. So summarize, like I mentioned, changes the observation level to be a broader level. So it returns only one row per group. and whatever you were grouping by before is now your keys. And you'll be sure that it's your keys because it will only give you back one row per combination of the key variables that were grouped by. So I had person year data, which had 2 rows per person, right? It was Ramesh, Dave, and Whitney in 2014 and 2015. I group by person, and then I'm going to use summarize. So I know I'm only going to get back 1 row per person. My new key variable is just going to be person. In fact, year is going to go away entirely, unless I specify some way to keep it. So I want the mean income for that person, and I want to know how many years I was tracking the person. I'm going to use N here to count how many rows there were of that person. And I get back that David's average was 103,000, Ramesh's was 81,000, Whitney was 136, and they were each tracked for 2 years. Oh, where'd we go? Oh, it just skipped a bunch of slides. What happened? Here we go. Okay. All right. That's everything that we have on going from tidy data to analyze data, which mostly was just going through how to use the different dplyr verbs. And there are, of course, many other functions that we can use to screen data. And I'm going to go through a couple of things in particular in regards to manipulating particular variable types. But those are the dplyr verbs. Are there any questions about that? Ooh. Ice cold coffee. It's weird that iced coffee is good, but cold coffee that used to be hot is terrible.
I'm drinking hot chocolate, so I'm nice and warm.
It's just really cold down here in this basement. Okay, all right. So let's move on. Variable types. So that is how we can manipulate variables in general, but often we are working with particular types of variables that will require specific functions to help us deal with them. So how can we combine those dplyr verbs that we have to actually create the mutate and summarize commands that will do what we want them to do? A lot of data cleaning is really just taking a variable that's already tidy and making it usable in some way. So there are 4 really common variable types. There's more than this, but these are the ones that pop up a lot. There's numeric variables. There are character or string variables. There are factor variables, which are just categorical variables. They can only take one of a particular limited set of categories. And then the bane of every data wrangler, date variables. They're terrible. I hate them. Everyone hates them. They're terrible in every language. So first of all, how can we figure out what types of variables we are working with in the first place? Sometimes you think that you have one data type and it's in fact another. So remember from before, we used this pivot to give ourselves tax data that was in the right format, but all of the columns were character or strings, right? And we didn't want that. So first thing we think about is how can we convert and check different types of variables. So one thing we can do, how can we check what kinds of variable types we have? Well, if we just print out a tibble, it will show us, right? So if you, this is one thing that tibbles do that data frames don't. It tells you the variable type of each variable. So this tells us that every single variable here is a double. Double is a type of numeric variable. Doubles, reals, floats, integers are all just different types of numbers that have different levels of precision, right? Integers only have whole numbers, and then doubles, floats, and reals are just different levels of how many different points after the decimal place do they allow. I don't remember exactly which ones are which, but you know, often you don't have to worry too much about it, unless you're working with really big numbers. So that's how we can check what our variable types are. We can also use vtables, I mentioned before. This will tell us the class of variables. So these are all numeric variables. You can also, if you want to, for some reason, you can use the sapply function. I want to take my empty cars data. I want to apply to each column in that data, the function, class, and it will tell me the class of all the variables. If you like that, you can do that. Okay, so that's how we can check. We can also check if variables are of a particular type with is functions. There's a bunch of is functions in R that just check whether an object is of a particular type. So I can say, hey, is numeric the empty cars MPG data variable? Yes, it is, right? So I can say empty cars, poll MPG is numeric. Yes, it is. Is it a character? No, it's not, right? So I can use is to check whether it is of a particular type. I can also use as to convert into a type, which works for most types. Sometimes you can't do certain conversions. So person, let's say I want to turn that into a factor variable. I can do as.factor on the person variable. I want to turn income from a string variable into a numeric variable. I can use as.numeric. I can do the same thing for deductible and AGI. So now I have the variable types that I want. Person is a factor variable. Income and deductible and AGI are all numeric now. Some notes about numeric variables. As I mentioned, numeric comes in multiple different formats based on the level of precision that you want. There's integers, doubles, and so on. Often you don't have to worry too much about it. R will often just convert the number into whatever format you need at a particular time. One common problem with this that you might run into, though, is if you have a very big integer. So let's say you have an ID number. You're working with some data, and it's got an ID number for a particular observation. It's like a 15-digit number. So with some, especially data reading functions like read Excel or read CSV or whatever, it will see that 15-digit number and say, oh, you know what? I'll just make that a float. And so I'm going to look at the first, let's say, 12 digits. I'm going to store those, and I'm just going to say, you know what? This number actually has 15 digits, but don't worry about the precision all the way down there, which is a problem, right? If you actually do need all 15 of those digits because it's an integer or because it's an ID variable. Sometimes if you read in a very big integer, it will store it in scientific notation, which A, most people don't know how to read, and B, will drop some information that you need because it's an ID. You can avoid this by specifying the call types arguments in your data reading function. So for example, in read Excel or read CSV, there's a call types, which you can look at that big giant number and say, actually, you know what? Treat that as a string variable, please. And then it will keep the whole thing rather than chopping off for precision. All right, let's talk about string variables. So string variables you can specify with single. Oh, go ahead. Sorry.
Could we quickly go back to doubles and dates? Even in your class when I was doing the data cleaning and changing months into just like the numbers and removing the specific days, whenever I did like date parentheses, I put in like my year or my month column, it would always turn up as doubles rather than as a date. Like the column wouldn't be labeled like a date type variable if it was just a month or a year. But if I had like month and year or the full three types of things in that date, then it would be labeled as date. Yes,
so I'll get to date variables in a minute, but R does not have a native year-month data type for dates. It has to be year, month, day. So it will not recognize as a date if it's just year and month.
Okay, I see. Thank you.
I believe in some packages there are year, month variables, maybe in the zoo package, but not in regular R. Okay, strings, characters and strings. These will pop up a lot, even if you're not actually working with text data. Especially if you're working with raw data, a lot of that will have to get read in as strings, even if it's numeric, because it's got stuff in there that R does not know how to recognize as numbers. So some basic stuff on working with strings. So first of all, we can specify strings with single or double quotes in R. This is actually very handy because this allows you to put quotes inside of strings very easily. This can be very hard in some languages. So I can say hello, right? That's a string. I can say hello with double quotes. That's a string. I can put that in quotes. I can see I got my single quotes, and then inside those single quotes, I'm gonna put some double quotes, right? And it will interpret the quotes that are inside the string as being actual quote characters. So if I've got, let's say, a data set of businesses, I can say, you know, Macy's. I'll use double quotes, Macy's, right? And it recognizes that this is in fact part of it and not the end of the string. So that's really handy. You can also get quotes in there with backslashes. Backslashes are what are called escapes. So if you have a special character in there that R wants to think is code, but is actually not, you can put a backslash before it, and often it will recognize this is actually part of your string. So that'll work too. You can use paste to stick strings together. The difference between paste and paste zero, by the way, is just in the terms of the defaults that they use. Paste will by default put a space between the different things that you're sticking together. Paste zero will not. That's it. So I can do something like paste H and LO with the underscore separator, we'll stick them together. H and LO will come together with a underscore between them. So it'll be H underscore LO. Often in data wrangling, the way that one way that strings pop up is that messy data will often default to being a character string because it is the most general of the variable types. It can really store anything. For example, if you have a 1,000,000 in your Excel sheet, sometimes the R will be able to parse that as a number, but sometimes it can't. Sometimes you'll actually just get a 1,000,000,000. It will not recognize this as a number. We're going to talk about how to work with this kind of string variable in a minute. And there's a lot of good string processing stuff in R. We'll come back to that. What are factors? Factors are another variable type. They're for categorical data where you're in one category or another. The factor function lets you specify those, and these are more efficiently stored than character variables, because if you were storing literally the words, let's say that our categories are 50 to 100K, less than 50K, and et cetera. If you just store the actual string, 50 to 100K, less than 50K, blah, 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 it would have to store all those characters in your data. But as a factor variable, it can just store 1, 2, 3, 4, and then elsewhere it will know that the number 1 means less than 50K, right? So it can store it more efficiently. And also, there are a couple of other things that, if you're working with categorical data, it's good to let R know that it's a categorical variable so it knows how to handle it properly. So we have a table here. I've got some data, some just regular character data. These are just strings at this point. So I've got 50 to 100K, less than 50K, 50 to 100K, 100K plus, 100K plus. I'm going to turn it into a factor with the factor function. I'm going to specify the levels. This is going to tell it what order these factors go in, which not all factors have an order, but this one does. So I'm specifying levels. So I'm saying that less than 50K is the smallest value, 50 to 100K is the next, and then 100K plus is the biggest. So then I can sort by income, and it knows the order to sort in because I've told it the order that this factor variable goes in. So it knows to put the less than 50K first, followed by the 50 to 100s, and then finally the 100K pluses. Next, dates. Dates are the scourge of data cleaners everywhere. They are hard to work with. There are date variables, there are date time variables, there are different formats of date time variables, there are multiple different formats. You can work with seconds or milliseconds or days or months or years. I'm not going to go super into detail here, but I strongly recommend using the LubriDate package. It will solve most problems for you. I guess I'll do a couple notes from the LubriDate package. So LubriDate, annoyingly, is part of the Tidyverse, but it's not in the Tidyverse package. You need to load it separately. So LubriDate makes it easy to specify dates. So I can say do year, month, day, 2020-01-15. And now that is a date variable. I can do operations on dates. So if I want to know what is 1 month after this day, I can say plus month 1. And now it's, plus months 1. Then it's the next month of that day. And it will do the best that it can to figure out what 1 month from today is. So for example, if I say, what's 1 month after the 31st of the month? Well, that should be February 31st, except that doesn't exist. So what's LubriDate going to do with that? It's going to say, I don't know. It knows that it shouldn't find anything there. I can ask what next year is. Right? You can do all sorts of stuff. I can get a range of days. I can do plus days. What's tomorrow? Great. That's the February 2nd. But what's today through next week? Right? I can get a range of dates like that. I can pull information out of this date. I can say, what year is it in this date? 2020. What month is it? And these are numerics now. These are no longer dates. Great. There's something else I was going to say. Maybe not. If you're working with date data, it is a pain, and that you probably want to use the LubriDate package. It does a pretty good job at picking dates out. If you have, in whatever weird format they're in, and you can specify how to look for them. So if, for example, you knew that you were working with some European data and you got, this right there, you might say, oh, well, hold on a minute. I know that in Europe, instead of month, day, year, it's day, month, year, usually, right? So I would say, okay, give me this, but look at it as though it's day, month, year, and it will properly account for that. All right. For dates, I will recommend going to this Lubridate cheat sheet. It will have most of the information that you want. And then, you work with it and you see how you can get it to go. Back to strings, though. There's a lot of information about how to process strings that will come in very handy when you're working with data wrangling. Some things are straightforward. You can, for example, use case when to fix typos or misspellings in the data. There are a lot of other functions that we can use for cleaning and splitting strings. For this, we're going to be using the string R package, which is in the Tidyverse. There's a cheat sheet here, but I'm going to go into more detail. So the first thing you might want to do is get substrings from your string data. For example, let's say that you're working with nested IDs. So for example, let's say that you have an NAICS code, industry code. Those are 6 digits long, but the different chunks of them have different meanings. So for example, you have the first 2 digits are the general industry, the next 4 are more specific industry, then the whole 6 digits are the most specific designation of industry. Let's say I want to pick out just the first 2 digits of that, and it's stored as a string. Well, I can use str_sub from the string R package. I give it the string that I have. I tell it what character position to start at and what character position to end at. So here, for example, string sub of hello, start at position 2, go to position 4, goes 1, 2, 3, 4, and gives me back ELL, right? So I can use string sub in that way. I can use negative values to read from the end of the string. So this is a pretty useful trick because there are a lot of cases where you have a big long string and you only need the end of it. So for example, if I give hello and I start at -1 and then I leave the next argument blank because that's just saying go to the end of the string, then that's going to give me the O from the very end of hello. Here's an example of using string sub in action. So here are some census block groups. Census block group is a census designation of geography, and they're in a city. They're usually about the size of a city block. They're very specific, and they're 13 digits long, and they're chunked up in a particular way that tells you some information. The first 2 digits are the state, the FIPS code for the state. The next 3 digits are your county code. So these first 5 digits tell you the state and county that you're in. After that, we get the census tract, and then the census block group when you include that last digit in there. So I've got this census block group data. I'm turning it into a string so that I can work with it a little bit easier in this case. If you want to pick particular value positions of a number, sometimes it's easier to turn it into a string. In this case, it's very important to turn it into a string because we have the problem of leading zeros. If you have an index number, some sort of identifying key variable that includes important leading zeros, then you want to include that. Why? Well, if I turn this into a number, this 0 here is going to get dropped, and we're just going to see this value here from the 1 on. And so if I want to get the first 2 digits as my state code, I want to make sure that it's 0, 1, right, and not 1, 5, right? Don't want to make that mistake. So I'm going to turn it into a string, and I'm going to use case when. So if this is 12 characters long, I want only the first digit. And if it is 13 characters long, I want the first 2 digits, which I can do with string stub 1, 2. I'm checking how long the string is with nchar. This tells me how many characters are in the variable, in the data. And the reason why turning it into a character to work with it like this is nice because it lets me check whether or not I'm working with a 12 or 13 digit number, which is nice because then I can know how many things to get from the start. And then I get the correct state indicators here. There's some other nice things that we can do with strings. There's a lot of data that you might find that tries to stick multiple pieces of information into a single cell that you want to split out. So string split will often do this. So for example, let's say I have a variable here, a string here that's A, comma, B, and I want it to be 2 separate things, A and B. I can use string split to split on the comma. So wherever it finds a comma, it's going to break it up into multiple things. And so this will produce a list for us. We usually only want the first element of that list. This will give us back A and then B as a separate thing. We can actually take a shortcut on this if we are in data that's already tidy and we just have a single variable that has multiple things in it that we want to separate into multiple columns, which is often what you want to do. There's also the separate function in tidyr, which is in the Tidyverse. So here's an example of some data. I've got this first observation, which is sales and marketing all in one cell. and then HR and marketing, again, all in one cell. I want to split them up into 2 cells, one for whatever was listed first, and then one for whatever was listed second. I can do that with separate category into category 1 and category 2, splitting on the comma. So where it finds a comma, it's going to say, okay, this is the first thing, comma, this is the second thing, here's the first thing, comma, this is the second thing. And now we have 2 different columns as we needed. You might also need to clean strings. You have a string that's got some dirty stuff in it. So for example, I mentioned before a number being read in with commas in it. You need to get rid of those commas. There's a bunch of different things that we can use to clean up strings for use. String trim will remove white space, so extra spaces at the beginning or end of the string. String squish will also remove extra spaces in the middle and just break it down to 1. So string trim with this right here will be, it's got an extra space at the beginning and at the end. String trim will get rid of those extra spaces at the beginning and the end. If we also have 2 spaces in the middle here, if we had used string squish instead, that would be collapsed down to just one space. Another one that I use all the time is string replace or string replace all. This is really handy, especially for getting rid of unwanted characters, which are in the context of data wrangling, often what you get. Often you'll get data that like it's read in improperly, so it's got a bunch of like junk characters in there, or it's got commas and numbers or something like that. So here we have some numbers that have commas in them. I can use string replace all to take the number variable and replace all the commas with nothing. Then all the commas are gone and I can turn them into numbers as they should be. All right, we're still on strings. The next thing I'm going to mention is a bit more complex, and hopefully you don't have to do this, but sometimes you do have to do this, and that is using what is called regular expressions, which is the terror of everybody who works with strings everywhere. What a regular expression is it's a way of describing a pattern in the text in a way that a computer can recognize it. Technically, this is what was happening when we did string replace all. It was looking for the pattern comma, and wherever it found a comma, it said, hey, here's a comma, I'm a computer, I can recognize this comma, and I can replace it with what you want. However, things can get a lot more complex than that. There's a whole guide here if you want to get complex, but I'm just going to give you a quick example and some common things that are used. So anywhere where you're telling R to look for something in a string, it is usually going to be a regular expression. Sometimes that regular expression is really simple, like look for a comma. This is a regular expression. Sometimes it's more complex. If you want to say look for a variety of things, you need to tell it how to look for that variety of things and identify them. So for example, if I say this in my regular expression, it will look for any digit from 0 to 9. If I do this, it will look for any letter, either capitalized or uncapitalized, something from A to Z in non-capitals, something from A to Z in capitals. A star will repeat whatever I'm looking for until I find the next thing. It's really hard to condense into a couple slides, but this is just to let you know you're there. And if you do have to do this, you can look at this guide. Here's an example of using a regular expression. So let's say that I have some companies that are publicly listed. I want to indicate that they are publicly listed, but I also want to get rid of their ticker symbol, which is in the company name in the data right now. Separate won't do this for us, not easily. So we're going to use a regular expression to look for the ticker symbol so we can get rid of it. So what does a ticker symbol look like? Well, it starts with a parentheses, and then it's got a bunch of capital letters in a row. So I'm saying look for a parentheses, look for a capital letter, continue to look for capital letters, right? The dot star means continue to look for whatever you just looked for until you find another parentheses. And then if you found that, open parentheses, a bunch of capital letters, close parentheses, that is what we're defining as a ticker symbol, okay? Let's look at that in action. So here I've got some company names. I've got Amazon, which is Amazon Holdings, ticker symbol AMZN. I've got Cargill Corporation, which does not have the ticker symbol in it, but does have a different parenthetical. It says cool place for some reason. So what I'm going to do, I'm going to create a variable that tells us if it's publicly listed by looking for a ticker symbol. I'm going to use string detect, which just looks for a regular expression or some other string inside of a string. Look in the name variable for a parentheses, a bunch of capital letters, and then close parentheses. Do we find it? Here's a parentheses, here's a bunch of capital letters, here's a closed parentheses. Yes, true, we are publicly listed for Amazon. How about Cargill? Here's a parentheses, but I don't see a bunch of capital letters, and then there's a closed parentheses. This one is not, false, not publicly listed. Then I want to get rid of those ticker symbols, so I'm going to use string replace to find those ticker symbols and then replace them with nothing. And so you can see that Amazon AMZN Holdings just turns into Amazon Holdings. Cargo Corporation does not change because it didn't have a ticker symbol in it in the first place. All right. That is working with individual types of variables, things that we can do with those kinds of variables. There's, of course, much more than this, but this is, I think, a good place to start. Any questions about any of this?
Just a quick question on this pattern in strings. What if the C in cool or P in place were capitalized? Would it have removed cool place?
That should be fine because this is looking for a bunch of capital letters in a row followed by an end parentheses. And so if it finds something that's not either a capital letter or an end parentheses, it should say, nope, we're done.
Got it. Thanks.
I will say, by the way, irregular expressions are aggravating for many reasons. One, the syntax for them is kind of weird and it takes a while to get used to. It's definitely something that you want to dedicate some time to learning if you're going to learn it. Two, there are many different syntaxes for regular expressions that differ slightly across different languages and even sometimes across different functions in the same language. So regular expressions in Python work slightly different from regular expressions in R. Regular expressions in the Tidyverse work maybe slightly different from regular expressions in other parts of R. Regular expressions in Perl, which is where they came from, right? Perl, are slightly different from all the other ones, right? But the differences are so minor that you think you've got a regular expression that works, or maybe you find something on Stack Exchange and it's like, doesn't quite work in your code and you need to modify it a little bit. So that's a little bit aggravating. Notice also, by the way, these backslashes here, that is telling the regular expression to, hey, this parentheses, that parentheses have a special meaning in regular expressions. They tell you what kind of characters to look for. But here I want to look for a literal parentheses. So I'm using those backslashes to escape the character. Another aggravating thing, before when we escaped a character, we only needed one backslash. Here we need two for this regular expression. So go figure. Any other questions? All right. Next up, we're going to talk about using data structure in our data cleaning procedures. So we've talked many times about how data wrangling is all about taking information from where it is now to where we want it to be. One difficult thing with this can be moving data from one row to another, because tidy data is particularly poorly set up for doing this. This is actually something that maybe wide data is better at doing sometimes. So this can be very important when you're doing something like calculate growth from an initial value, right? But we can often solve this with the use of a range and then things that reference particular rows of the data. We already talked about this a little bit. We're going to go a little bit more into detail on it. The important functions here are first and last, which refer to the first and last row, of course. So here's some data. Here's some ticker data for Amazon and Walmart. Here's the date of those ticker prices, and here's the stock price for that ticker on that date. So I'm going to arrange, I'm going to sort the data by ticker and date. I'm going to group by ticker. And then I want to calculate how much the stock has grown since March 4th, which is the first day in the data set. So how can I do that? Well, I've grouped by ticker. So it's going to do Amazon and Walmart separately. And I'm going to say, take the stock price on today's date, divide it by the first stock price that you see, which we know was March 4th because that's the first date in the data. And we sorted by date. So the March 4th is going to be up top. So the first stock price that we see is March 4th. So we're going to divide the current stock price by the first stock price and then subtract 1. So we see that on March 4th, clearly there's no growth since March 4th. No big surprise. By March 5th, there's a little bit of growth. By March 6th, there's even more growth. Right? This is all comparing to March 4th from there. There's also the lag function, which instead of looking at the first or last rows, looks at rows relative to your current position. So a lag will, for example, look at one row above. Or lag 2 will look at 2 rows above. Lag -1 will look at 1 row below. Okay? You do want to be careful with this. It has the same name as a lag in like time series, but it's not the same thing. Time series lag would be looking at one time period ago, and lag in dplyr will look at 1 row above, which sometimes is one time period ago, but often is not. So let's say I want to look at the stock growth since yesterday. So daily price growth will be stock price divided by the lag of stock price, which is yesterday's stock price, and then subtract 1. So the first row here gets a missing because there is no yesterday in the data here, right? And then here we have the same value that we had before, oops, because it is, again, comparing to March 4th. And then this one now compares to the day before. So this is seeing how much the stock grew from the 5th to the 6th. There are trickier things that we can do with this data structure. So for example, let's say you don't want the first row in the data or the last row in the data. You want something at a different position. Let's say that I want to get growth since the 5th, which is that middle date, which can be tricky, right? What can I do? Well, I can just use a tricky sort. So I can sort by ticker, and then instead of sorting by date, I can sort by whether or not the date is the 5th. What will this do? This will say, okay, is the date the 5th? True if it's the 5th, false if it's not. I want you to sort by that. Sort will go from false to true, and I want it to go from, put the true one on top, so I'll go minus that date, right? So this whole rigmarole here is for the purpose of sorting by ticker and then putting the 5th on top, so that when I use first, I'll be referring to the 5th. For more complex stuff like that, it's often really useful to use case when to create a new variable. And then you can refer, and you can store data that just has data from wherever you want, and you can sort of propagate it to the other rows. What do I mean by this? So here's some data from test scores. So we have some different people in different grades, and they got their test scores in different subjects. Okay. So let's say that I want to compare your test score in math, or let's say I want to compare your test score against the average math test score. Okay. I can't just group by subject and then get the average, because then I would get the science average in science, I'd get the English average in English, I'd get the math English in math. I want the math average everywhere, right? So what can I do? I can use case when to create a new math scores variable that only contains the test scores if it's a math test, okay? Everyone else gets a missing. Then I can group by grade, and then I can get the mean of math scores using missings, because there are a bunch of missings here. I told there to be missings for all the science and English ones. And once I do this, I now have the average math score in that grade, and every row can see it, right? Because I took just the math scores, and it was missing everywhere else. And let's not get rid of the last column there so we can see it. So you can see what happened here, right? I took in each grade, so here's math in 6th grade. It's a math score, so I'm going to store it over here. Here's math in 7th grade. It's math score, I'm going to store it over here. These are not math scores, so they get missings. Here's math in 8th grade, 85, right? Then I'm going to take the average within grade. So here, the average math score in 6th grade is 80. So every 6th grade observation is going to get it because I grouped by grade. Here's the average math score in grade 7. Every 7th grader is going to see that, right? Because I grouped by grade. So in this way, I am propagating information from some rows to the rest of the rows, which can be handy in a lot of cases. All right, any questions about data structure stuff? All right, there's still more to go. Yeah, this is the last sort of section of new content if you're getting overload. Automation. So I mentioned way up top, you want to let the computer do as much as possible, especially if you have a lot of different rows to go through. You want to, or a lot of different columns to go through, a lot of different files to go through. You don't want to necessarily be doing that by hand. Not only will that create a lot of tedium and work for you, but also you're more likely to make mistakes, right? You know, I've done data entry projects before, and you always need 2 different people to do the same data entry so you can check each other's mistakes, right? Because there always are going to be mistakes, no matter how careful you are. So you want to automate as much as possible, meaning you want to use the same code applied to all of your different things. You don't want to be in a situation where you're just like, okay, load this data set, run these 3 lines of code on that data set, load this data set, run these same 3 lines of code on this data set, where it's all in a different thing. Because, well, what if you want to change something? You got to go back to every single time you wrote that code and change it every single time. And it just wastes a lot of effort as well. So we're going to talk about 3 different ways to automate. One is using the across function, which is new in new versions of dplyr. We're going to be writing functions, and we're going to be using per, which we've already used a little bit before. So first, the across function. Across is what you want to use with dplyr when you have a lot of variables and you want to apply the same function to a lot of variables at once. Okay. Older versions of dplyr used what are called scoped variants of the functions, where you have mutate at, mutate if. I preferred these, honestly, but they're gone now, or at least they're not preferred now. You want to use across instead. So across basically allows you to use, if you remember those tidy select things, right? We use like tidy select starts with, or all the different parts of select. Like we could say, I want to select the variables from 1 to 5, or everything but this variable. You can use all those select tricks to pick the variables, and then you can use across to apply the same function, or multiple functions even, to all of the variables that you've picked. Okay, so that's what you can do. There's also some, I'll talk in a second about row-wise calculations as well. But across, so we have our stock data that we already had with Amazon and Walmart. So what I'm going to do is I'm going to create some, both of these price growth variables that we had before, and then what I want to do is I want to convert them into basis points. Okay, so basis points are the percentage growth, but on a very different scale. I just need to multiply by 10,000. So how can I do that? Well, I'm going to take all the variables that start with price growth. That's price growth since March 4th, price growth daily. So in this case, I'm not saving myself that much typing, but I could just write out both the variable names. But if I had like 8 of these variables or 100, this would be a lot easier, right? Then I want to apply the same function to all of those variables. I want to multiply all of them by 10,000. And that's what will happen, right? So instead of the percentage growth that was 0.0038 or something like that, now I have 38.8, which is the basis point version of the price growth, right? So I took starts with and a function, and I used across to apply that function to all of the variables that qualified for that. In the typical version, you can see that we replaced the original values. So the price growth since March 4th and price growth daily have just been replaced with these new values. You can create new variables that work as well. You can do .names, which will say, if I want to do, it's too much. I'll get that in a second. So you can say, okay, I want to keep those original ones, but I also want to have like price growth basis point version, right? Put that in the name. I can keep both of them with the .names function, or the .names argument. You can also use a list of functions to do multiple calculations at the same time. Let's do an example of that. So here we have, again, across, which starts with on price growth. We're going to apply it to both of those variables. I'm going to create 2 different versions of the variable. I'm going to create a basis point version and a percent version. So the basis point version multiplies by 10,000. The percent version multiplies by just 100. I'm going to give them new names of just the column that I'm working with. So price growth daily, price growth since March 4th, and the function that I'm giving it, which is either the original or the basis point version or the percent version. And then just for simplicity to show it to you, I'm only going to keep the price growth version. So here I have the original price growth daily. Then I have the price growth basis point version, which multiplies by 10,000, and the basis growth percent version, which multiplies by 100. So I can apply multiple functions to multiple variables all in once with one easy automated function. Another common issue with that you can solve with across is if you want to apply the same transformation to all variables of the same type. So for example, if you want to convert a whole bunch of variables to numeric, let's say, you can check which kind of variable you're working with by using the where function. So if you remember, so let's say that I want to convert, if you remember a while ago, I wanted to convert a bunch of different variables from character to numeric. I could do that with this approach here. In this case, I'm going to convert all of my numeric variables that are already numeric into pounds. So they were dollars. I'm going to convert them into pounds by dividing by 1.36. So I'm going to use across. I'm going to identify which columns to work on by checking which ones are numeric. So I'll say where is numeric, and that will check all the columns to see, are you a numeric variable? If so, I want to convert you into pounds. And once I've found those columns, I'm going to convert them into, create a new version of them that is converted into pounds that uses this function where I just divide by 1.36. All right, so that's how we can use across to do multiple different, the same operation to multiple different columns at once. We can also use the row-wise and C across functions to do a single calculation that combines a bunch of columns. So a common thing that you might see in business data is values that are recorded a bunch across a bunch of categories, but each category is in its own column and then not report the total, and you want the total. That's annoying. So here's how we can do that. So here we have some data that has the year. It has the sale, the amount of revenue generated by sales, by marketing, and by R&D. And I want to get the total spending, but it's not included in the data. So how can I add up all those columns to get total spending? First off, I'm going to tell it to do a row-wise operation. And then I'm going to create a total spending variable that sums across the different columns from sales to R&D. So C across is column across. It says work across all these different columns and do a sum. If I did a sum normally, it would try to sum across the rows, but because I'm row-wise and using C across, it will sum across the columns instead. And then I'm going to convert it. I'm also going to create a percentage of total spending variable using across as well. All right, so that's how we can use across to automate some dplyr stuff. More generally, we can automate things by writing functions. Generally, if you have the same chunk of code popping up in your code multiple times, you should probably write it into a function that you can just reference repeatedly. This will make it a lot easier if you need to go fix something later or change something that you feel want to change. So if you're going to do something more than once, you generally want to write a function. The general structure of functions in R is that you have a function name. A function is an object. You're creating a function object, and you create it as using the function, which takes arguments. So here is the first argument of our function. We can set it equal to the default. So if we don't specify the argument, it will take that default, second argument, and so on. We do some code in here. We can refer to these arguments, more code, and then we can return the result. And then it will, if we do that function, it will give us back. So let's do a very quick example of a function. Let's say it's our add2 function. That's going to take a number. Let's make the default number 2. And this will be a function. And it will just be my result is x plus 2. And then I'll return the result. So what's this going to do? First of all, if I just say add2, what this is going to do is it's going to take the default number that I've given it to. It's going to add 2 to it, and it's going to give me back the result, which is 4. What if I give it, let's say 105? It should take that 105, add 2 to it to create the result, and then give me back the result, which is 107. Right? That's sort of the basic idea of how functions work. Some tips for writing functions. First, you want to think about what types of values your function accepts, right? Do I want it to take numbers? Do I want it to take strings? Make sure that what it returns is also consistent so that you know what you're getting. You don't want to write a function that sometimes gives you back a string and sometimes gives you back a number because it'll be harder to use. There's way more that I can cover in 2 slides here. And so look more broadly and try stuff out. If you find yourself doing something a bunch of times, you could do worse things just taking that chunk of code, sticking it inside a function, and then calling it regularly. Something to point out with functions in R is that you can use unnamed functions. Something you might have noticed in the across examples is that I used this. I said function x times 10,000 without saving it as a function like I did here, right? Instead, I just had function x times 1,000. This is called an unnamed function where I don't save it. I just sort of slot it in somewhere. If your function is only going to be used once, there's nothing wrong with this. You can just sort of slot it in like we did here. And what I'm referring to is back here. Right, so here I did across. What function do I want to apply? I want to take x and divide it by total spending, right? I didn't name this the divide by total spending function. I just sort of plopped it in there and it will be applied. In R4.1, by the way, not only are we introducing a new pipe, the bar pipe, but you'll also have this shortcut notation instead of having to write out function x every single time. It's really nice. All right, the last part of automation we're going to cover is per, which we already talked about a little bit. So per is basically a replacement for for loops. For loops in R are surprisingly slower than most other methods of looping over stuff. Unlike in, let's say, Python, where it uses for loops all the time. In R, you generally want to avoid for loops if you can. I mean, they're not the worst thing in the world, but there are better ways to do stuff. One of those ways is using per. What per does is it takes a vector of stuff or a list, and it does some sort of function to each of the elements of that. And it pops out a list of the results at the end. Map will usually generate a list of objects. if you want it to specify, give you back a vector of results, you can do map underscore double for a numeric vector, map underscore character for a character vector, map underscore df for if you want to take a bunch of data sets and pop them together. It just sort of iterates through something, applies a function to each of those things, and then that's it. So I mentioned before using the sapply thing for class. You can also use map character. So I can take person your data, send that to map character. It will iterate over the different columns of the data and check the class of each of the variables. So the person is a character variable, year is a numeric variable, income is a numeric variable as well, and it's giving back to this as a character vector. We already used this to process in many file names, as in our reading in files example, where we used a list of files. We passed that to per to read them in one at a time using the file reading function. And then we passed that to the processing thing that processed each of our data sets and then finally squashed them all together with bind rows at the end. But there are many other ways you can use this. For example, let's say I have a summary profile function that I've written that does a summary of all the data in a state. So let's say that I take data, I'm going to pull out my state variable. I'm going to get all the different values of state that there are, all the different unique values, and then I want you to iterate over all the different states and run my summary profile function. And you can generally use per in place of most places where you would use a for loop. All right, any questions about automation? We are nearing the end here of the lecture section anyway. All right, so we're going to finish up and then we're going to move on to an example. So some final notes to things. Like I said, we can't possibly cover everything. This is such a broad topic with so many tools in it. And my goal here really was to sort of show you what's out there so that you know what to look for and you have some good tips for things to use in particular situations. There's almost always going to be more documentation reading when it actually comes time to use this stuff. But there are some final notes I want to give you. How do you save your data once you're done? Once you're done wrangling all your data, you're going to want to save it so you don't have to run everything from the start every single time. You've probably learned about the save function. Save can save many different objects. It basically saves a workspace, and you can load that workspace back into your global environment with load. I usually instead, if I'm working with a single data set, will use the save RDS function instead, which saves a single data frame. And it can't save multiple objects, it just saves one. But you can then read back in with read RDS. Why do I prefer save RDS to save? Because it is better compressed. And also you can load it in like this. Load will load in all of the objects into your environment, whereas this lets you, let's say, read in a data set and assign it to the name that you want. Whereas save and load will give it back the variable name or the data set object names that you already had in the first place, which sometimes is not what you want. If you want to share it with somebody who's not using R, you can use something like write CSV, which makes a CSV. There you go. Also, I do want you to please document your data. You don't want to go through all the trouble of data wrangling something and then leave it for a couple months and then come back to it and have no idea what any of your variables are. At the very least, keep a spreadsheet that keeps a description of what all the variables in your data mean. That would be important. You can also label the values directly. If you use the SJ labeled or Haven packages, there are ways of labeling the variables themselves, where you can add a label to the variable. Then when you use something, you can then look at the labels of the variables with those same packages. Also, the vtable function in vtable will print out the labels of the variables if indeed they are labeled. Vtable will also allow you to generate a documentation file that you can share. So let's take a quick example. Library SJ labeled. So here we have some data that is labeled. So here you can see the variable names are not particularly descriptive, but this person has thoughtfully put in labels on the data, so we know what they actually mean. You can read them. vtable gave us a table that lets us see how all the variables relate to those values, and there's also a file option, so you can save this table so that you can then share that documentation information with other people, save it with your data so you can look at it later. Okay, that is all the information that I have for you. We're going to now work through a walkthrough of some data that we can clean. We may or may not get through the whole thing. Data wrangling is a process that can sometimes take some time, but we're going to do what we can. So what I'm going to do is I'm going to show you the data. I'm going to show you the goal that we have here. And then we're going to sort of try to figure out what we can do on, and I'm realizing I did not put up the actual, I gave you all the data, but not the file that goes with it. I did not. Oops. All right, sorry about that. You need to re-download that data because it'll have that file in there for you. So what do we got here? We have a bunch of different folders. These all have folders, are folders of data from different sources that we want to combine into a single data set. This is a very common thing that you might have to do in a data wrangling setting. What are our data sets? So we have data from IPEDS 2018. IPEDS is a government data source that looks at information on colleges. So it has things like, what is this college's endowment? What's its enrollment? What's the makeup of its students? That sort of thing. From both 2018 and 2019, we have these files here for that in the IPEDS folder. Great. These are, looks like Stata data sets, which is how the IPEDS data is provided. We will have to use a read Stata function from a special package to read those in. What we want to get from these data sets, we want to get the percentage who are currently in distance education. We also want to get the tuition share, which is this equation right here. From the 2019 data, we want to get whether the college is a private or public college. What else do we have? We have the EADA data. What this is going to, in the inst level data set, this tells us whether the college is Division I in sports or not, which has there's a classification code right here. If it's 1 through 3, they are Division I. That's an Excel file. We'll need to read that in. We have some New York Times data. This has the COVID cases by county as of July 31st. Oh, sorry, it's got a bunch of different dates, but we want to get the dates, the data from July 31st. And we've still got it. We're still going. Plenty of data sets. We might not get through this. We have the this file right here, which has population by county in 2019. You can see here we've already got some string cleaning up that we're going to have to do. There's that weird period at the beginning of that. Then we have some data from a package, the political data House 116 data, which is going to give us the congressional DW nominate scores. And let's skip the last one because I also did not upload that. So we're going to try to combine all these data sets together. And so let's try to walk through this together. So any ideas, first of all, where should I start? What's the first thing that I should do before trying to put all this stuff together? Any thoughts?
Set your directory.
That's a good place to start. We can set our directory. One thing to note, I generally would recommend against setting the directory in the code itself, because that means that when you send your code to somebody else, they're not going to be able to run it. Instead, you're going to want to set your working directory using RStudio directly. I often will do, it's a source file location, which happens to be this folder here where everything is being stored. Great, so we set our directory. What else can we do?
Get an idea of what we want to end up with.
Great place to start. Yeah, so let's get an idea of what we want to get up with. We want to create data with observation of one observation per college per day. And so we got a bunch of different data here. We have data from colleges, right? So this is going to be college level data. So from IPEDS, it's going to give us college level data. Our key variable there is going to be college. From the EADA, we also have college level data. Great. From the New York Times, we have cases by county by day. So we have county by day data. So we're going to need to figure out some way to combine college with county by day. With the census, we have county level data. From political data, we have congressional district data. So what we want to end up with is one observation per college per day. I guess the day stuff came from the foot traffic panel. Let's forget the day part. One per college. we want one observation per college. So we can think about what kinds of links we're going to need to put together. We need to get a college to county link to link up IPEDS and EADA with the New York Times and the census. And we need a college to congressional district to link up IPEDS, EADA with congressional district. And then once we're done, we're going to have one row per college that we're also going to have information in there about the county and the congressional district. And then we're going to have values that have whatever we're pulling out from IPEDS and EADA, as well as the county cases and the population and the nominate scores. All right, cool. We know what we're looking for. What's the next thing we need to look at? The golden rule of data wrangling. Look at your data. Let's look at our data. So let's just look at what our data looks like. So we already looked at this one. So we got some county data. So we can see, first of all, as somebody already mentioned before, we have two header rows. We're going to want to skip this first row when we read in census. We've got a county names that are in text format. It doesn't look like we have any sort of numeric county identifiers. So we're going to need to clean this up. And then we have some wide format data with population in each of the years. All right, so that's what our census data looks like. What's the next one? Let's look at our sports data. So here we have unit ID, which is maybe is going to be our identifier. We have institution name, and then we have our classification code. Looks like we are already in tidy format for this data, and we have our unit ID as a possible link. Oh, and then the census, we had textual county level data and skip first row. All right. What else do we got? We got the IPEDS data. Uh-oh, it's in Stata. I can't open it. In this guy, I have Stata on this computer, so I could open it, but instead we're going to read this in so we can look at it. So we're going to do library Tidyverse, as we do, library Haven. It's going to have a Stata reading function in it. So we're going to have IPEDS 2018. Read DTA to be in the IPEDS folder, and it's this one. Okay, so now we can look at the data. Okay, so it looks like we have tidy format. There's unit ID again, so that's great. So in our IPEDS data, we have unit ID. So we know how we can link colleges between IPEDS and EADA with that unit ID. So that's good to know. What else do we have in IPEDS? Looks like we have, what do we need actually? We need distance education and tuition share. So we have the formula for tuition share, that's handy. What do we like? How can we find distance education? Let's look at our variables because it looks like they're described. So we have variable labels here. We can see them sort of written up here, institution name, survey year ID. So now we can see the labels. So we want to look for distance education. If they didn't have the variable labels, the data would hopefully come with some sort of documentation alongside it that we could look through. So let's use find in page. Let's open this up in the browser. Distance education, there we go. Percent of students enrolled exclusively in distance education courses. What is it we wanted? We wanted percent in distance ed. So that's probably going to be these two variables, right? Because we got exclusively and some but not all. And those look like they're just their own variables by themselves on a 0 to 100 scale. Okay, so that's good to know. How about IPEDS 2019? Look at that one as well. There should also be a unit ID. Yep, we're good on that. And for this one, we just wanted whether it was a private or public college. So we can look for that one. let's see. Uh-oh, this is not telling us exactly what our variable is. Now I can tell you that the sector variable here is what we are looking for, but it's not labeled. So we would have to then go back to the documentation to figure out which of those numbers from 1 to 8 corresponds to a private institution. Which I don't remember off the top of my head. We'll pick one at random and say that that's the one. All right, what have we not looked at yet? I think we looked at everything except for political data. So let's load that up. So that one's in a package here. So we're going to load political data. We're going to get the House 116. So it looks like here we have the congressional district. Or no, that's the Congress number. Oh, we have the state and the district code. Cool. And so then how can we link that up? Let's go back to our iPads and see how we can possibly link up those two things. Do we perhaps just have a congressional district in here? There we go. Congress district, the congressional districts. We just have that in there so we can link that up as well. So now we found out sort of where our things are. So got unit ID, link to iPads with congressional district. Okay, so now we're going to load in some files and do some cleaning on them. So let's start out. Where should we start? Any thoughts about what file we should look at first? Preparing it to merge with the others.
Probably iPads and EADA since they got the unit ID.
There we go. Yeah, that should be an easy merge. All right, so we got iPads 2018 in there. What we need from it are the percentage distance education and the tuition share. So let's go ahead and create those variables and then get rid of everything else we don't need to merge it. The iPads 2018, we're going to read that data in. We are going to mutate to create tuition share. It's this right here, which if I didn't have this all typed out already, I probably would do something like a tidy select or a row across to create this sum here. It would be easier. And then I want the distance education, distance share. That's going to be the sum of those two variables that we had before. Let's type in 18%. There we go. Great. And now we only need a couple of these variables, so we can select just the variables that we need. So we're going to keep the unit ID variable. We're going to keep the congressional district variable because we know we're going to need that to merge in later. What was the name of that? Congressional. Where'd it go? Oh, there it is. Is it in both of them? It's not. See, that's interesting. The congressional district variable is not in the 2018 data. It's only in the 2019 data. So we're going to thankfully get that from the 2019 data and merge it with the 2018 data. Okay, so that's actually not in the 2018, so we don't need to worry about that one. Tuition, share, and distance share. We also need the county data so that we can merge. So county, FIPS, where's the county data? Is that also in this one? FIPS state code, county code. Okay, so yeah, so that's also just in 2019. Okay, so here we just have unit ID. We're gonna get all the geographic information from the 2019 data. So that one's simple enough. All right, let's do 2019 now. So for 2019, we just wanna get whether it's a private college. Dang if I can't remember. I don't remember which of those is private. Let's pretend that it is 2, because I think there's more private colleges than public colleges. Okay, so we're going to create private is sector. We're going to use a logical here. sectors 2. And then we are going to just get the stuff. That's all we need. So then we just need to get the stuff that's going to link together the files. We're going to select unit ID, our congressional district, our county and state. So Congress District CD, FIPS state code, and the FIPS county code. If we're forgetting anything, we've got the congressional district to link it to the political data. We've got the county and state to link it to the census. And we have the unit ID to link it to EADA and the IPEDS 2018. So that should be fine as well. All right. Next, let's do the EADA. So that's going to be an Excel file. So now we need to have our read Excel package. Let's bring that in. Let's see what it looks like after we read it in, because sometimes reading things in can mess them up. Looks like it came out just fine. Got unit ID, so that's good. And then we wanted the classification code for 1 to 3. So that was going to be division 1 is classification code. It's going to autocomplete, by the way. No? Oh. Classification code, okay. Use in to check whether it's in the values from 1 to 3. And then I'm going to keep unit ID and division 1. All right, we're steamrolling through this thing. Okay, we will soon get to the more complex stuff. Oh, so okay, so we've got these 3 files. We're going to be merging them together. Let's check that the merge works properly and see how well it does. So we know that we're going to be merging on unit ID for all of this stuff. Right, so let's check and see how many mismerges there are going to be. First of all, let's check and make sure that unit ID actually is our key variable. Right, so we're going to check if unit ID is key. So we're going to do IPEDS 2018, select unit ID, duplicated, max. 0, no duplicates. Great, good to go. Check 2019 as well. Also 0, good to go. Let's check EADA. Great, good to go. Anyone notice something that I could be doing at this point?
Creating a function.
Creating a function. I got the same code multiple times. So I can make myself more consistent. And I'm also going to have to do this in the future, right? So let's go ahead and make a function. So check dupes. That's going to be our function. We're going to need to pass it the data, and we're going to need to pass it some variable names. So one tricky thing about writing functions is that the Tidyverse functions are very good at taking named variable names and less good at taking strings. And for writing code, it's the other way around. It's very easy to write it to take strings and very difficult to make it to write names like this. So we're gonna have to use a different version of select that accepts. So I'm gonna have this be a string variable coming in. We're gonna do it that way. So we're gonna do our data, and we're gonna use select. I think they just changed the. They changed the syntax for this one. Is it just select? Forget if that takes. Let's see if that works. Trying something out and seeing if it works is a good way to check stuff in general when you're coding. Let's try select across unit ID, because I want to do this as a string. No, that doesn't work. Okay. Oh, right. of course. Oh, that does work. I don't know why I thought it didn't work. Oh, because I'm passing in a variable. God, it used to be so easy. And then they made it hard. Why did they make it hard? Yeah, deprecated, whatever. That's fine. We'll use it. No. There we go. Okay. So I mentioned the scoped versions that before that were deprecated. It's probably, God, there's gonna be this, what is happening right now is something that will happen every time you do data wrangling, by the way, where you're like, I thought that would work. Why doesn't that work? And then you got to go look. Clearly, I'm still not fully used to across yet.
Professor, will you be posting this code, like the example?
Yeah, the
that
code
you're
up here.
typing up?
Yeah.
All right, cool. Thank you.
Hold on. Oh my God, that just works. I don't know why I didn't think that worked. It just works. That's easy. Okay, great. So I don't need to do anything special. I was working way too hard at that one. Great. Okay, so we're going to take our delay data. We're going to select the varies that we send in. We're going to do duplicated, and we're going to do max. And actually, I don't actually need to do a return here. The one thing about R functions is that whatever the last object that you've given R, it will return that by default if you don't have a return function. So this will just give me back this thing. So do that. I'll do check dupes iPad 2018 unit ID, no duplicates. Great. And then 2019, also unit ID, no duplicates. And check dupes E80A. Great, no duplicates. Okay, we're good to go. Okay, so next, let's do New York Times. Let's see what we can do with that there. So that is a CSV file, I believe. Yeah, Microsoft Excel, comma separated values. That's an Excel file. We're going to use the county cases there. Now we're going to do New York Times. So we have New York Times is based on the read CSV function. Which, by the way, I'm using read CSV here. There is a much faster way of reading in CSVs, which is the fread function from the data.table package. I'm not going to do it here just to keep everything consistent in the Tidyverse, but I would recommend using fread instead of read CSV, even if you're not using data.table for anything else. It's just wildly faster. But this data is small, and let's keep it simple. Okay, let's take a look at how that read in. So we have county, we have state, we have FIPS. So that's going to be how we can link to our FIPS codes, because we don't just need to make sure that the variables are there. We also need to make sure that we know how to link them together, right? So in the case of the iPads 2019 data, right, if we select FIPS and county code, right, we can see that we have the numbers. Oh, cool. So this FIPS code apparently does not just include the state, it also includes the county, right? So because it's 4 to 5 digits long. So that's going to match up perfectly with this FIPS column right here. We don't need to do anything. I thought that this was going to be state, so we need to split this up into state and county FIPS, but we don't have to. If we weren't going to do that, though, let's say that we wanted to do that, we could do something like this, where we would say mutate fips equals as character fips, mutate state fips equals stir sub 1, 2, county fips equals stir sub fips 3, 5. Right, and then that would split it up into 2 different things. And because we seem to have leading 0, 0, I guess already a character that works pretty well. Something I should point out, by the way, when you are working with dates and converting them, or dates or index variables and converting them strings back, another good function is stir pad. What stirring pad does is it basically allows you to do something like add back in a leading 0. So let's say that we had a file name that was like this. Let's say it was like stored like a 2020/01/01/sales, right? And I have I have a bunch of these folders, and I want to pick out this particular data set, right? So I want to pick out the data set by date. So I've got a different data set for each day, and I want to say pick out the data set for this date and this date and this date. I've got a date, and that date is load the library. Let's move this downstairs. I've got a date. That date is 2020/01/01. Great. So I want to convert this into this right here. And let's say that I actually don't have that. Let's say that I have my year. I know that I want it in 2020, and I've got my month. I want that to be the first, and my day. That's also 1. Okay. So I've got these 3 values, and I want to use them to find this file. Okay. Now the problem with that is that I can't just paste them all together because there's some zeros in there. So there's some padded zeros in there. And I can't just add a 0 on there because what if it's the month October? Well, then I don't want it to be 0, 1, 0, right? Enter stir pad. So I can do str pad of, let's say, month. I want it to be 2 wide, add to the left, add a 0. So now month becomes 0, 1 instead of just 1. So I can paste this all together. I can say paste, or paste 0, the year, then the slash that I want in my file name, then the stir pad month, give us a 2-digit month, and then the dash, or the slash, sorry, then the stir pad day, and then the slash, and then sales.csv, right? And then that is something that I can actually read in. Anyway, back to New York Times. Turns out the FIPS was just fine. We didn't need to mess with it. So then we can use it to, we'll be able to use it in a minute to merge things together. Other thing to note here is that nicely, this New York Times data has the names of the counties, which is really handy because if you remember, the census data did not have the FIPS code in it. It just had these county names in it. So we can use the county data that we have in here to link everything together. So as I remember, we wanted data just from, what was it, July 31st. So we're going to filter just to that day. And what's the date variable? It's date. Date equals, oh, I guess we do need the lubridate data set or package. So we want it to be 2020, July 31st. And I think that's all that we need to do. Everything else should be ready to go. Well, looks good. Okay, so now we have New York Times data. And then we have our census data. This is going to be the tricky one, I think. So we got census, read CSV, this census file here. Gonna have to do a little bit of cleaning on this one. So let's take a look at it, see how it read in. So first of all, oh, we had that first row, which we didn't want. So we're gonna need to skip that first row. Skip equals 1. There we go. Now we have it properly named. Now we wanted population in, when was it? 2019. So we have 2019 population over here. We have now, if we wanted to get population in every year, we'd want to do a pivot to long. But here we only want that one column anyway, so we don't need to bother with that. In fact, we can get rid of all of the other years except for 2019. So we can just select county and 2019 to work with. But we're also going to need to clean up this county variable because we want to merge it with the other stuff. So what are we merging with? So we know that the county name information was in the NYT data set. So we need to look at what these look like so that we can put them together. So in the census data, we have a period, the name of the county, the word county, comma, the state. In the New York Times, we have the name of the county, the state as separate columns, and it does not include the word county. So we have some other stuff in here. Looks like in Alaska, they have weird stuff because Alaska does not have counties in the same way that other areas do. I believe New Orleans is the same way. So let's take a look at New Orleans and see how they treat that. New Orleans has parishes. Oh, not New Orleans. Sorry, Louisiana is the state that New Orleans is in. It's been a long workshop. Okay, but it looks like it says St. Bernard there. How does Louisiana look over here? Has the word parish in here. Does not have the word parish in here. So we're going to need to add the word, we're going to need to deal with the word parish and county, depending on whether we're in Louisiana or not. We're also going to need to deal with Alaska. So we saw that Alaska, Alabama, and if you're thinking, how did I know to look for these things? It's because I've worked with county names before. Some of this stuff you just got to get used to. All right, Alaska, it finishes out the word borough here, or area. It looks like it's inconsistent, but I think it was the same in the New York Times data. I'm doing all this scrolling, but I don't really need to. I can, oops. View, New York Times, filter, state. Okay, it looks like it fills out the whole name there. So that's easy. So it looks like Alaska is fine, but we need to not mess with the word in Alaska because it already matches. The Alaska word already matches, except for the state part at the end. Louisiana, we need to get rid of the word parish. All the other places, we need to get rid of the word county. We still need to split up the state from the comma or combine them in order to work this out. Okay, so what can we do? So we might want to keep this New York Times version of it where it's all split out because that will usually be easiest to work with. So I can do something like limit it just to the state of Alaska. So, but I think it's going to be easiest to put together this version than to split apart this version to get the New York Times version. So I'm going to use the New York Times and then have a target of having it match the census is what I'm going to do. But I am going to get rid of this leading period because that just doesn't help us any. So I'm going to take the census. I'm going to use string sub to get rid county equals string sub county. Just start with the second one, go to the end. That should get rid of that period for us. Great. So now we need to match thing, then the word county or parish or nothing, and then comma, and then the state. Great. So we can do that with the New York Times data. Okay. So New York Times, what are the variable names? We have date, county, underscore in lowercase, state, and FIPS. So I'm going to rename the census variable to be full county name or something like that. I didn't mention this function, but rename will let you just rename a whole function. So let's do county and state. It's county. And then I can create the county and state variable in the New York Times data. Okay, so we're going to use a paste. We want the paste to be the county name that's in New York Times currently, then nothing or county or parish, then a comma, and the name of the state. So the first thing we're going to want to do is we're going to want to paste in the county. Great, easy. And actually, I'm going to get rid of the paste here. I want to have a space between. No, I don't. I don't want to have a space between. Okay, county. Then I want to have a space before the word county. But I want it to sometimes be county, sometimes be parish, sometimes be nothing. That sounds like a job for case when. So if the state is Alaska, then give me back Nothing. Add nothing. If the state is New Orleans, God damn it. If the state is Louisiana, then give me parish, and that's how you spell it, right? Always look out for spelling errors in this kind of thing. Parish, great. Okay, and then if it's anything else, then give me the word county. And I do want to, I want a comma after each of those actually. Because then that will parish, comma, yeah, okay, great. Then after our nothing, parish, or county, I want the state. And that, and they are written the same in both, right? They're all first letter capital, Louisiana, Alaska. Look, that looks like they're good to go. Okay. Cool. We've got county and state now constructed, right? This is the kind of string manipulation that you tend to do when you're data cleaning. Okay. So extremely important when you just done something like I just did is you want to make sure that it worked properly, right? Look at your data, check if it worked. So how can we do that? Well, one thing that we can do is we can just check how many values in one of these are not present in the other. So what I'm going to do is I want to check the county and state values. So what I'm going to say is I'm going to say, okay, tell me, take the NYT data, and I want you to just keep the observations for which county and state is, you could use that not in thing that you had before. I'm going to use an exclamation mark around some parentheses, is in census, county and state. So now I've just got the observations in the New York Times county and state variable that don't match anything in the census version. And then I'm going to pull the county and state variable. And then I'm going to give all the values that don't match. Let's see what we got. Oh, no. Ah, because I missed a space after the comma. See, that's the kind of thing that you don't notice if you don't check. Still didn't work. Oh, okay. But it's all unknown county, Puerto Rico, and some other things that shouldn't have had county appended to the end of them, and some weird spaces here. Okay, so this is the kind of thing that you would then have to spend several hours fixing. And you'd have to go one by one and be like, okay, this unknown county, what should that be? Okay, oh, I noticed, okay, this one's got a space after. I need to get rid of that by hand. And that is what is going to take up a lot of the time in data wrangling. For now, we're going to ignore it and just say, you know, good enough for now. But that is the kind of thing that you want to check. So you want to know that that problem is there so that you can fix it. Okay, so we have everything there. So now we have our matching variable in the census. We only need that variable and the 2019 population. So I'm going to select county and state. And I want to select this 2019 variable, but the problem is that it's a number. And so I just put in 2019. It's going to be like, you don't have 2019 variables in here. If you want to refer to a variable name in dplyr that shouldn't be a variable name, just put these backticks around it. And then suddenly you'll have it. So now our census looks like this. I'm going to rename again. So I'm going to do population equals 2019. All right, now we're ready to merge. So we can merge some stuff. So we have our 5 different data sets that we can merge. Let's do some merging. Oh, I guess we should check our keys as well. Check dupes. Oh, I didn't do the political data. We got 9 minutes left. Let's skip political data for now. You can come back and do it later. You have all the tools to do it if you want. I'll also upload the foot traffic data in case you want to do, oh, maybe I shouldn't do that. Yeah, we'll figure it out. Okay, check dupes for NYT. It should be county and state. No duplicates, great. Check dupes, census, county and state. No dupes. Excellent. Nothing has duplicates. Now we can start the merge. Fix the county and state thing. We're not going to do that. Merge. So let's start by merging together all the unit ID variables. So let's do iPads 2018. We're going to merge. Oh, we're going to left. So the thing with merging is that you do want to check how many things did not merge properly, because there's almost always going to be stuff that does not merge. And the join functions actually make this kind of difficult to do. They're not super about how many observations you're dropping when you do a merge that misses some matches. There's a couple of different ways to do this. One is you can use the tidylog package, and this will do things like, say, when you do a merge, it will say, hey, you just dropped this many observations, just letting you know. So tidylog is a good way to do that. Let's do it that way. Have I even installed tidylog on this computer? I'm not sure that I have. Okay, so we're going to do let's do a left join with iPad. Actually, let's do an inner join. Let's just get the matches. Now, I'm not going to say what it's going to merge on, which might actually be a problem here, because if I had kept more variables, but I only kept the only one that they share is unit ID, so that should be fine. It will just guess that it's going to merge on unit ID. Okay, let's see. Inner join. 3 columns, rows that are only in X, 0, rows that are only in Y, 0. Everything matched. Cool, we're good to go. This is the part that tidylog is adding. If I had not loaded tidylog, this would not show up. It would just give me the result. Okay, next, let's bring in the EADA. Next one. Uh-oh. So it looks like we have 1,700 observations in iPads that are not in AEDA, and 47 that are in AEDA but not in iPads. So at this point, we need to figure out what we want to do about that. Are we just going to drop all the ones that don't match? Are we going to keep them but without without Division 1 information? Let's do that. Let's keep the colleges, but just have missing Division 1 information. And then there will be some, but we're not going to have any colleges that only have Division 1 information and nothing else. So we're going to do a left join to just keep the iPad stuff and not the EADA stuff. Cool. So then we can merge in New York Times and Census we're going to merge in the New York Times with the FIPS data. It was the name of it. So let's check inner join with NYT. Oh, incompatible types. So in one of the data sets, the FIPS is stored as a character variable, and the other one is stored as a numeric variable. So we're going to need to fix that. So first of all, let's figure out which one is which. So class iPads 2019 FIPS. This is the numeric. Okay. So that must mean that the New York Times one is the character one. Let's change that to numeric so we don't have to worry about leading zeros. So we can actually change the New York Times inside of this function here, and it'll work just fine. So we're going to do mutate FIPS equals as numeric FIPS. Let's try that. There we go. Oh, none of them matched. Nothing matched. Okay, so we must have some other fundamental problem between the FIPS in iPads and the FIPS in New York Times. This sort of thing is completely normal to run across. So what do we got? Oh, FIPS is just state. That's why I don't know why I thought that wasn't true before. Okay. Oh, okay, it's 2019. Oh, maybe what I was looking at was the county code. Ah, the county code has the full FIPS. There we go, there we go, there we go. You can see the labeled values here. So what we're gonna wanna do is we're gonna wanna rename so we have the county code variable in iPads, which has the 5-digit FIPS code that we need. And we have the 5-digit FIPS code in New York Times, but it's called FIPS. So what we're going to do is we are going to rename county code as FIPS in New York Times. And this might still give us a type problem. Yeah, we have a type problem still. And then we're going to mutate county code as numeric county code. There we go. Okay. So we still have a lot of mismatches. In this case, I'm not so concerned about that. Here's why. We have some mismatches where the county code in the iPads data does not show up in New York Times. It's a little concerning, but it could just be that some counties the New York Times is not tracking. The other way around is definitely not a problem, because if a county does not have a college in it, then it's not going to be in our iPads data, because that's a data on colleges, specifically four-year colleges. So that's not a concern for me necessarily that we are missing all of these ones right here. Again, let's keep all the colleges, and maybe just some of them won't have data on cases. Great. Okay. Now, finally, we can merge in the census data, which we're doing on county and state. By the way, I haven't had to specify by on any of these because there's only been one possible set of things to merge on. But if there were more than one and you didn't want to merge on all of them, you definitely want to specify by. All right, finally, we're going to check what's going on with the census. And that one seemed to work. As we already found before, a lot of those county state things didn't line up properly. And so that would be something we might want to go back and fix, because that probably should not have been a problem. But we had that. Let's do this on the left as well. Our data. And there we have it. That is a relatively clean version of the data that we need. We could go a step further and add in the foot traffic data that I talked about at the very top here, or the political data, which would require us to merge on congressional district. But that is the process of taking a bunch of files, merging them together, cleaning them up to the point where we need. And this is a relatively simple thing. Most tasks that you actually have in the real world will be a bit more complex than this, but this is, I think, a good exercise to start on. So a good exercise at this point: take the data, try to replicate and I'll add this code to the GitHub. But take this data and try to replicate what I've done, and maybe add in those new data sets without looking at the answer, and just see what you can do. All right, that is it. Thank you so much for coming.
Thank you very much. This was really helpful.
Glad you liked it.
Thank you, Professor.
Thanks, Professor.
See you.